So we're going to switch gears now, and we're going to talk about another sort of major topic, which is policies. And we'll do this sort of across 3 lectures. So we'll have some introduction, and we'll do a funner example with this lecture, and then we'll go into browser policies, which is an implementation of the ideas of secure policies or procedures. So policies, procedures, processes are sort of different words for the same thing. A lot of, they make security work. So they're not a technical subject necessarily, but there's a lot of vulnerabilities that arise if you do not get the policies correct. Generally, when we go back to Stride and we think about policies, this usually tends to fall under the E in Stride. Which is escalation of privilege. So E is, or escalation of privilege, it sort of, it connects directly with the idea of authorization. So different people are authorized to do something or to not do something. And if you're able to do something that you're not authorized for, but you're able to find maybe like a different path that you can take, that lets you get access to something that you're not authorized for, then we call that escalation of privilege, okay? And generally the reason why that other path existed, or that sort of loophole existed, is because there was a flaw somehow in the policy. So we've seen examples before, or I sort of reordered these lectures so they may be examples that you will see, but when we talked about social engineering, we had this whole story, a true life story about someone whose username was @Matt. And there was this policy that Amazon had, which basically said, we're going to do really strong authentication if you want to reset your password, but we're not going to do strong authentication if you want to add a credit card to your account. And that was like sort of the turning point of the story, right? Like the attack was based on that idea. When we talked about, or we will talk about SSL certificates, HTTPS, there was this whole procedure for validating domains where, I would send an email and the email would go to admin@domain.ca for the domain that you were trying to register. And so that's a procedure. It was chosen by the certificate authority. They could have chosen different procedures, and different CAs implemented slightly different procedures, and it led to vulnerabilities, right? So like, for example, someone would accept emails. They would accept challenges that were sent to an email like SSL certificates at domain.com. And most of the world didn't know that that was a special email address that you're supposed to set aside and not hand out to users. Like anything, any attack or threat, it's usually never like purely one thing or another. So it might be social engineering to get you into the server room, but then it turns into a more technical attack once you have access to the server room. So policies are the same. There's a flaw in the policy. It could be a component of the attack. It lets you sort of progress your attack further, but it's not necessarily, an attack that's 100% policy driven. Now, why I like talking about this subject in this course is there are things that we have good methodologies for, and there's things that we don't have great methodologies for. And so this is an example of something where it's very sort of ad hoc. So people kind of make up arguments for why they think a policy is secure, but there's no like systematic way really to go through, or at least it's not done in practice. We'll talk about in theory what you could do at the very end of the lecture. But for now, there's not like a clear sort of methodology. And so I like to put my finger on these things that don't have clear methodologies as well, just to encourage you to, in a class like this with this topic, to think about what the methodologies would be and what are some ways that we could improve the methodology. So today, or in this lecture, we will do some quick examples, And we'll also do a kind of larger example that concerns airport security. And then in the subsequent lectures, we'll look at two more like technical policies. Both of them are in the browsers. One of them governs how browsers control cookies, called the cookie policy. And the other controls how browsers isolate JavaScript that's running on a website from other resources that may also be running on that same website, or your view of the website from your browser. So that's called the same origin policy. Okay, so let's jump into some quick examples. So a few things that, or one thing that you've definitely seen is a password policy. So a password policy is, you have to choose a password. It has to have this length. It has to have a certain number of special characters. It has to have capital letters, numbers, that type of thing. So these are policies, and we will not let you register if you don't meet the policy. So that's the actual policy itself. The password policies are sometimes a little misdirected in the sense that the reason these rules exist, like what are they trying to do by making you use a special character and a capital letter and a number, is they're trying to make your password harder to guess. So it uses a broader set of possible characters. Okay, but you could generate, let's say you just had numbers, like your password was just a pure number, but if it was truly randomly chosen or machine chosen, pseudo randomly chosen, and it was long enough, it could be just as strong as some other password that's, say, only 8 characters or 6 characters, but has all these like mix of characters and things like that. So anyway, so the exact intent behind it and what it actually achieves are not necessarily the same thing. There are some really bad passwords that would meet all the rules of a password policy. Maybe it's based on a lyric or some sort of pop culture reference, and so it's just basically a saying, that happens to have a special character and a number in it. A better approach, by the way, for password policies is to grab a copy of the password and check it against a database of every password that's been leaked. And then if you see that it's been leaked, then you say, no, sorry, you can't register that password. We've seen that password before. But anyways, privacy policies or terms of service, these are things that you see on websites, usually at the very bottom in fine print. If you click on it, it's a bunch of legalese, but it explains sort of like the data that the website can collect about you and what it can do with it and things like that. There was a story when Facebook first turned on two-factor authentication. So when you logged into Facebook, you would now get a text message. It would be sent to your phone. This was sort of before, authenticator apps and things like that were popular. So you would get this second factor. It was sent to your phone, and then you would log in. Okay. Now, this at first glance looks great for security, right? It improves security. So now if I able to steal your password somehow or guess your password, I also need your phone, or at least control over your phone number in order to get that second factor. So security it's now harder for me to break into your account. However, there's also a privacy angle. Okay, Facebook now has a phone number. It's a phone number that belongs to a device that you control. So it could conclude that with high likelihood it's your phone number. And they also know it's not like some old phone number. It's something that's in use because you have to be using it in order to log in. So this is valuable data. Facebook is in the business of sort of building dossiers on people and what all the information about them. And now they have a phone number, a validated phone number for you. And so that can, as a piece of data, if they sell it, or they augment it with, say, data from other sources that are based on phone numbers, then they can, they can monetize it. They can serve up better advertisements and things like that. There was another story about something that was added to Apple's iPhones. It might exist in Mac software as well, and I'm pretty sure it's still active. There was a lot of news when it was first announced, and then I don't see a reason why they wouldn't necessarily keep it. But the basic idea is that so you have a camera on your phone, you take pictures of lots of things, and it was designed to basically suppress or try and combat like exploitative, like sexually exploitative images or videos of children. And so what it would do is it would use kind of like machine learning. So the neuro is a reference to neural nets. So this is like AI. And it would use that algorithm to examine every single picture. And if it looked like it could possibly be child pornography, then what Apple would do is not allow you to keep that picture. And then it would also sort of report it to law enforcement somehow. Okay. And so that's a policy. So it's a policy that surrounds cameras. And like all policies, there's always a chance of false positives. Okay. So cases where someone had legitimate style pictures or legitimate pictures that they were taking that were somehow being matched, even though they weren't illicit images at all. So, for example, the one in the newspaper was about a father who had a son or daughter, I forget, and their child had a rash, and the father took a picture of it, sent it to the doctor, and then this was flagged, and then law enforcement came to his door later, and it obviously wouldn't result in charges because there was nothing criminal that happened, but still you have to deal with law enforcement as a result. Another example is URL address manipulation. So this is a URL, so you can take a look at it. What do you see? So you see a domain, right? attackbank.com. You see a resource that's being loaded. It has a file name, an extension .asp. So this is like a dynamic resource. And then what you see is a question mark. And usually what happens, we'll actually talk about these URLs later when we talk about browser policies. But this is a parameter that's sent to the website. So when the website receives this URL or it receives a request for this URL, it kind of has the parameters it needs in order to sort of put into this script, and then it's going to return something. So a URL like this might look like, for example, maybe there's a profile number. Okay, so I'm profile 5741. If I click on this, it's going to show me my profile page, right? Your profile page would be something different. Okay, now what if I went here and I changed 741 to 742 or 743? What would happen? Well, it depends on how the website is configured, right? In some cases, it would say, well, you're trying to view a profile of someone and you're not logged in as that person, so we're not going to show it to you. Okay. Sometimes these numbers would be so long that they would be difficult to guess. So it might be a hot link that just takes you directly to that profile. And if you could guess the profile number of another user, clicking on that link would be enough to see their profile, but it would be so long that it would be hard to guess. Okay. And then the worst kind of websites are ones where these are just sequentially assigned and you don't have to be logged in to see the profile. So if I change this to a 742, I'm looking at someone else's profile. If I change it to 743, I'm looking at someone else's profile. All right. So that's a policy that's set in order to display profiles this way. There was a criminal case where somebody, I think it was for AT&T, they basically, the company implemented exactly this, like the simple version, the dumb version. And so the person would just, if you just change that number to some other number or the next number, you would see someone else's profile. And everyone's profile had, I think it was like maybe a bill, wireless bill or something like that, but it would have your name, it would have your address, your phone number, maybe some other information. And so the person actually built a little script that would just try every number and then kind of download the data. And they got charged, and they got charged under hacking. This is in the United States. And their defense is, well, I'm just changing URLs, right? It's not hacking. I mean, I'm not breaking into information that I'm not supposed to see. It's a public URL, right? And it turned out actually that person was convicted of hacking, and it was less about the URL and it was more just about the fact that they wrote a script to do it automatically. It seems like if they had just typed it in one by hand, that maybe the case would have went a different way. But anyways. Another example is what we call swatting. So SWAT teams are they're law enforcement or police. They show up into to deal with situations, and they're called when the situation is like high tension. So think of like someone holding someone a hostage or some situation like that. You can tell they're SWAT usually because they come looking more like military soldiers than police officers. So they'll have like full gear on and automatic weapons and, bulletproof vests and those kinds of things. And so there's a policy, which is, let's say you call in and you say there's a very violent crime that's happening right now, right? The police could try and make a decision about whether you're telling the truth or not. Or they could have a policy of, we're just going to show up assuming the worst, okay? Because we don't want to be the police that said, oh, that sounds like maybe it's a prank call, or maybe it's, maybe it's not a real situation, a real urgent situation. It turns out it is a real urgent situation. They don't want to be in that position, okay? And so what they'll do is they'll respond to any like credible sounding call, as if it's exactly as the person is describing. Okay. And so what people would do is they would report crimes at other people's houses. They would call up and say, oh, I'm at this house, even though they're not. Right. And this is what's happening. And what they do is they would try and get the police to show up. And then it's very disruptive, as you can imagine, for the people that are living there. Right. You have police, they're knocking down your door. It's a high tension situation. They have guns. Sometimes mistakes are made, shots get fired, things like that. And so it's a very dangerous situation as well. And so that was a sort of, it was a kind of attack that people would do on each other if they could figure out what your home address was, particularly like online communities. If you made someone angry, they might try and do that if they could get your home address. Another example concerns AirTags. So AirTags are these little devices. They look like a coin. And what you can do is you can add them to your, it's like a device. You can attach it, put it in a pocket of a bag, put it on your luggage. You can get like a attachment that would attach it to your keys. And then if you lose these things, then what you can do is you can open up an app on your iPhone, and it will show you where it is. Okay. Now let's pause and think for a second. If you've seen an AirTag, great. If you've not seen one, currently, at least when I'm recording this video, think of it kind of like the size of a coin, like a large coin. That's roughly the size of it. Okay. How do you think this works? How is your iPhone able to tell where your AirTag is at a particular moment? Okay, so you might be guessing, well, there's a GPS in the AirTag. Okay, so that maybe that's true, maybe that's not, but a GPS isn't enough. So a GPS would be enough for the AirTag to know where it is, but in order for your phone to know where the AirTag is, it would also need to somehow communicate where it is across the network so that message would reach your phone. Okay, so it needs to know where it is, so GPS, and it needs some sort of network connection, so maybe 5G. Okay, so you might imagine an AirTag with a chip, a GPS chip, a 5G chip, which gives it satellite connection, and then it, or I should say, cell tower connection, and then it's able to track it. Okay, now you can buy tracking devices that are this, a GPS plus an internet connection, but they're way bigger than an AirTag. Okay, you can't fit that hardware, at least by today's standards, into something that's the size of a coin. Okay, so an AirTag actually has neither of those. It doesn't actually know where it is, and it doesn't have an internet connection. Okay, what it does have is a short distance connection called Bluetooth. And it's able to connect to some other device that's nearby, such as a phone. And then what it can do is it can rely on the phone to report where it is, because the phone has the GPS, and the phone can report it over, if it's connected to cellular or connected to Wi-Fi, it can report it through its internet connection. Okay, so an AirTag is sort of a dumber device. That's what makes the form factor so small, because all it's doing is it's connecting to a phone, and then the phone's actually doing the hard work of figuring out the location and phoning it to Apple, and then when you connect to Apple, you're able to see where your AirTag is. Okay, now the last question is, well, whose phone? Whose phone is it connecting to, right? If I leave my luggage, I mean, if the AirTag's with me, it's in my pocket on my keys, and my phone's in my other pocket, they're talking to each other, that's fine. But the use case is I forget my keys somewhere. Okay, so now my phone's gone. It's nowhere near my AirTag. Okay, and so what Apple did, this is their policy, is they said, okay, we control a lot of phones. There's a lot of iPhones in the world. And so we're going to set it up so that everybody's iPhone will sort of play this role for everyone's AirTag. So if your phone comes into the vicinity of anyone else's AirTag, then what it can do is it will play the role of figuring out the location and phoning it home and updating Apple servers where the AirTag is currently. Okay, and Apple's able to do that because they control a lot of infrastructure, and there's a lot of iPhones in the world. You're going to have a sort of privacy issue with that. So the privacy issue is that, your AirTag is talking to a stranger's phone, right? So what Apple will do is they'll hide it. They'll hide all this interaction, under the operating system, and so that you don't really have a way of seeing that this is happening. Okay, so that's how an AirTag works. Now, one of the problems with AirTags is stalkers will use them. So if you want to follow someone without their consent, then you might try and slip an AirTag into a bag or clothing or under a car or something like that. Okay, and so what Apple did is they said, okay, because this AirTag will be traveling with your phone, that's a situation that we can notice. We can notice that there's a phone. It belongs to person A. There's an AirTag. AirTag belongs to person B. They're traveling together. Okay, they're moving locations together. Okay, now that could be for any number of benign reasons. For example, my wife takes my keys with her. Right now, it looks like my AirTag is following her, but that's fine. All the phone will do is it will just give you a warning. Okay, so you can see what the warning looks like. It says AirTag found moving with you. The location of the AirTag can be seen by the owner. And if you click on it, then you get like a little more detail. And it also gives you the option of sort of disconnecting. So you can disconnect your phone from the AirTag. I guess you can disable, I'm not sure the exact technical details here, but it sounds like you could actually disable the AirTag and make it stop working. And then it won't follow you. Okay, so this policy is a lot better than just, you have the AirTags and there's no policy at all. Some people think it still doesn't go far enough. It's still easy to use AirTags to try and track people. But anyways. Okay, another quick example. So there's a nice paper called Security Policy Audits, Why and How. And they have a bunch of examples, and they also sort of point out the fact that, this is an understudied area. And I'll circle back to the paper again at the very end. But they have another example that they use as sort of the main example of their paper, which is SIM swapping. Okay, so first off, what's a SIM? Okay, so the idea is that it has something to do, it probably has something to do with cell phones. Okay, and so basically what happens is everyone has a phone number. So this is unique. It's assigned to you by your phone carrier. So I'm with Bell in Canada, and so Bell is my telecom provider, and so it gives me a phone number. All right. Now, let's say that someone calls that phone number is going to get routed to Bell. Okay, so but everyone knows that this block of phone numbers is controlled by Bell. Now, what Bell's going to do is they want to make my phone ring. Okay, but no one else's phone. They have lots of customers. So how do they make my phone ring? Well, they have to know which phone is mine. Okay, and so what they'll do is they'll give me a SIM card. And the idea of a SIM card is that it basically it's programmed with my phone number, and I put it in my phone. And so now there's a binding between my phone number and that phone. Okay. Because it's a card, at least now there's virtual ones, but before it was like literally a card. You could pull it in and out of your phone. Let's say I get a new phone. What I can do is I can take my SIM card out of my old phone, put it in my new phone, and now the new phone is ringing instead of the old phone. Okay. If I lose my phone, I lose the SIM card as well. Then I got to call up Bell, and what Bell's going to do is they're going to assign my phone number to a new SIM card. They'll give me a new SIM card and say, okay, we have to map your phone number over to the new card instead of the old card. Okay. And then if you have more than one phone number, you could have more than one SIM card. And so sometimes when people travel and they're worried about like paying a lot of data because they're in a different country, they might get a SIM card that's local to that country. Now, what they did in the paper is they would call up telecoms, and they experimented with lots of different telecoms. So they tried it across, it was 50 attempts, I assume over 50 different telecoms. But it might have been a couple attempts at each one. I forget the exact detail. And basically what they'd say is, hi, I'm so-and-so. I lost my phone. I have a new SIM card. Can you please patch my number to my new card? Okay. And so what the policy would be is before we do that, we have to make sure that the person calling is actually the person who controls that phone number. Okay. And so they found that in almost 40 out of 50 attempts, 4 out of 5 attempts, that they were able to get it changed even when they were impersonating the person who owned the account. Now, for ethics reasons, they were impersonating themselves. But basically, when they would call up, they would limit themselves to just information that would be publicly known about them, and then they would try and get it swapped. So there's a bunch of bad policies that result. Why were they able to convince the person that they were someone that they were pretending not to be? And so a great example of a bad policy is the following. They said, okay, if you are the true owner of this phone number, right? Tell me the last 3 phone calls that you received. And if the person's able to do that, then it must prove that they control that phone or that phone number, right? Okay, now put your adversary's hat on and think about how would you attack that. Okay, well, what the attacker could do is just call the number 3 times, maybe from 3 different phones. Now the attacker knows the 3 most recent calls. It was the attacker. Okay, and then they call really quickly after making those 3 phone calls. And then when asked what the last 3 phone calls are, they can report the exact numbers that they were. And they don't have control of the phone itself, and they're not the actual person themselves. They could be an attacker that's anywhere in the world. Okay, so the flaw here, if you want to put your sort of finger on like what exactly went wrong, is you're asking someone to authenticate, and in order to authenticate, you're trying to get something from them that's private or personal, some information that only the real person would know. Okay, but in this case, the adversary can control that information. So the most recent calls, it's not something that it's not actually personal information. It's personal in the sense that the person who owns the phone knows it. Okay, but what those 3 calls wasn't something chosen by the person who owns the phone. It wasn't something that was even under their control, right? It was under the control of the people that made those phone calls, and that person could be an adversary. Okay, and so the @Matt example is exactly the same thing. You were going to authenticate based on knowing the last 4 digits of a credit card, but if an attacker is able to add a credit card to your account, then they know the last 4 digits of one of your credit cards. Okay, so that last 4 digits is something that's potentially adversarially controlled. An adversary could add that information to your account. So you cannot base security questions on values that could be controlled by an adversary. They also go through some stuff on SIM recycling. So this is sort of like where actually forget if it's the phone number or the SIM number, but basically what happens is one of the two, people stop using one of the two, and then eventually what they do is they hand out that number to someone new, and then the person who it's handed out to gets all the stuff that's associated with the old person's account. There's lots of stories. I work a lot in cryptocurrencies, and so there's lots of stories about how people's Bitcoin or other cryptocurrencies were stolen using SIM swapping as at least one of the components of the attack. So usually it was maybe more than just that attack, but it usually comes down to some sort of two-factor authentication. If I do SIM swapping, now I get your second factor, and so I'm able to impersonate you. Here's another example I like. This is a story. This has to do with USPS, so the United States Postal Service. And they had this policy that was concerning what would happen if you change your address. Okay, so you lived in one house or apartment, and you have an address, and now you want to switch houses, but a bunch of your bills and stuff are going to go to your old house. Okay, and so you want to forward your mail from your old house to your new house. So the policy was anyone could submit a change of address form, and there was no authentication. You didn't have to prove that you were submitting a form about a house that you owned or will own. Just anyone could do it, and they would list the old address and they would list the new address. Then what USPS would do is they would send 2 postcards, one to the old address and one to the new address. And they would say, somebody's requesting that the mail from the old address be forwarded to the new address. Okay. Do you agree with this or do you not agree with this? All right. And so it gave an opportunity for either the person at the old address or the person at the new address to catch the fact that this forwarding was about to be set up, and to stop it if it was malicious, if an attacker was trying to get, say, your mail redirected to their own possession. Okay. Now, when you tell someone something and you wait for an answer from them, you have 2 policies that you can implement. Okay. You need a policy because what happens if you don't hear back? Okay. So if you hear back, do you assume everything's good or do you assume everything is bad? All right, so we've seen this before. It's called allow override or deny override. So allow override means that you just assume that everything's good if you don't hear back, and deny override would be that you assume that everything's bad if you don't hear back. Okay, so you don't make the change until you explicitly hear back that it's okay to make the change. That would be deny override, and then with allow override, you would send the postcards, and if you don't hear anything, or if the people say, yeah, it's fine, then you assume everything is good. Okay, so it would take someone explicitly saying don't do that for you to stop it. Otherwise, by default, you'll roll out the change. Okay, where have we seen allow override already? So when we talked about attack trees, we talked about revocation, and there were these certificate authority servers running this protocol called OCSP, where you could go and say, hey, is this certificate revoked? And a lot of times, at least historically, you wouldn't get a response back because the servers were overwhelmed. And so if you didn't get a response back, you would just say, well, do I throw an error? Does the browser throw an error? Well, if it does, then you're going to be seeing a lot of errors on the web. And so what it will do is it will just sort of opportunistically or optimistically send this hoping to get a response. And if it doesn't get a response, it's going to assume the certificate isn't revoked and everything is good. And that's a problem because the adversary can just drop the response and now you won't learn that the certificate was revoked in the case that it was revoked. Okay, so what's the attack for these postcards? It's the same attack. Basically, what you got to do is you got to drop, if one of these 2 people, right, especially the old address, so we'll assume that the new address in an attack scenario would be the adversary's address. The old address is the address of the victim. Okay, what they want to do is they want to make sure that whatever message the victim sends to USPS never reaches them. Okay, so they can try and attack it before the postcard gets to it. So maybe they sort of watch for the mail person to drop off the mail, and then once they see the mail get dropped off, they very quickly go and they grab it out of the box, right? Or what they could do is, if this person responds, they could try and cut that off if it's by mail, for example. Or what they could do is they could just do it maybe with 100 different addresses, and 99 of them, the person's going to say, no, don't set up that mail forwarding. That, I didn't authorize that. But for 1 out of 100, someone's just not paying attention. They miss the mail. Maybe it gets lost. Maybe it's, maybe they do see it and they are like, yes, I'll add it to my to-do list to cancel this mail forwarding, right? But then they just forget to do it. Okay. So there's a lot of opportunity here for something to go wrong. So this article was sort of exposing this policy, and then they had this example. So I'll just read it. In a particularly comical case from 2017, an Atlanta resident was arrested for cashing checks that had been rerouted from the corporate headquarters of the shipping giant UPS. UPS is not USPS. They're both in the mail business, but this is like, for parcel delivery, resulting in literal bathtubs of mail piling up outside the hapless fraudster's apartment. Okay, so basically what he did is he did this attack. He did it on the corporate headquarters of UPS. They probably didn't notice that postcard, right? You can imagine a giant corporation and all the mail they get. It's probably very easy for that postcard to get lost. Or maybe someone sees it and they're like, who do I give this to? Where does this postcard go? I don't know whether this forwarding is right or wrong. Right, I have to give it to someone. I don't know who to give it to, and it sort of gets lost. Okay, and then they add that it took UPS 3 months to notice that the mail wasn't showing up. Okay, so that's how sort of busy the operations are. That it was like 3 months later they realized that, hey, we haven't got any mail in 3 months. That's very unusual, right? And then they probably called USPS, and USPS says, well, your mail is being forwarded to this address. And then the police went to check on that address, and they like they said, they saw like a bathtub, was full of mail. Okay, so how can we fix this from a policy perspective? So the first thing we could do is we could go back to the very start where you fill out the form and there's no ID required. And we could say, okay, you need to prove that you have ownership or control or something over the address that you're trying to forward the mail from. Okay, if you can do that, then we'll proceed. Otherwise, we're not going to proceed. And the second thing is we can flip from an allow override to a deny override for the postcards. So we can do the postcard thing. We can send them. Maybe there's a little code or something on it. But both parties need to get that postcard and type that code into the website in order for that to be, in order for the change to be confirmed. Okay. Now, does this solve the problem 100%? Maybe not. So if I'm watching, let's say the attacker controls the destination address, they don't control the origin address, but they watch for the mail person to come. And as soon as they see that postcard, they go and they grab it out of the mailbox right away. Then they get the code, then they can fill it in on the website. And then they could get the mail forwarded. So deny override doesn't necessarily, prevent this, but it does add some level of security, or it's a slightly more secure policy than an allow override. Okay, so now what we're going to do is we're going to turn to a sort of larger example, okay, of a policy or a set of policies or procedures. So we're going to do an example that hopefully everyone has gone through the process of, which is taking an airplane ride or a flight somewhere. So when you think of airplane security, right, you probably think of the thing that we call security, which is when you're sort of going through the metal detectors or X-rays, and they are scanning your bags and they're scanning your person for items. Okay, but the security in terms of airline security, it actually starts a lot earlier. It starts at the moment that you purchase your ticket. Okay, so I want to fly to Bologna, for example. I pick out my ticket, I fill it out. Okay, now once I have my ticket, I paid for it. Can I give my ticket to someone else? I can't go anymore. Can I give it off to someone else? And the answer is no. Okay, so when you buy an airline ticket, that ticket is linked to your identity. Okay, so you cannot give it to someone else. You could cancel it and then rebook it under someone else's name, but that's technically a second purchase. Okay, it's not a transfer of your ticket. Okay, that said, it's not like, say, Expedia, or if I'm buying it directly from Air Canada, it's not like they're checking my ID. I'm doing this on a website. We don't have digital ID in Canada. I might say what my ID is, so I might put in my passport number, for example, but I'm just asserting that. They don't know that I have that passport or that my face matches the picture on the passport. So that's what we mean by an ID check, is just that there's a confirmation that the person doing this action matches the document that they're showing. Okay, so I just sort of assert what my identity is. I pay. And then what happens behind the scenes is that the airline will forward this name to the government. And what the government maintains is a list of people that are not allowed to fly, usually for reasons related to terrorism, or could be other crimes or things like that. And so they're going to check whether that's the case or not. And they're going to decide based on the name whether they're going to allow me to fly or they're going to deny me from flying. Okay. Now, I'm not going to learn what the outcome of this is until a little bit later. Okay. So this is just something that's sort of happening behind the scenes. We'll put a pin in it for now and we'll come back to it. Now, once I get my ticket, it is going to have a special 6-character code, which is called a PNR, passenger name record. Okay. You've probably seen this before on your ticket. Sometimes you have to type it in to various things. Okay. A booking code is another name for the same thing. And your PNR, you might not think of it like a password, but it is a password. Okay. If I know your PNR for a flight that you're about to take, and usually I might need something else, like say your last name, but I'm going to assume that I know that anyways. Then with just those two pieces of information, just not even talking to like an airline agent or something like that, like just logging into a website, I can usually just type those two pieces of information into the website, and the website will say, okay, what do you want to do? I see that you're Jeremy Clark and you have this flight. What do you want to do with it? And so I could cancel it. I could, try and get credit out for it. I could put in my frequent flyer points account instead of yours. It probably is going to show you my name and things like that, so you could just harvest that information. Okay, so these PNRs are they're actually sensitive information. It's like a password, and you should protect it. Okay, do people actually protect these? Well, if you walked around an airport, you know that people are often carrying their boarding passes in their hands because they have to show it at various points, and it's printed on the boarding pass, right? Usually in pretty big print. If they have a suitcase and they're pulling it and they already have it tagged, right? Usually the booking code is very prominently on the luggage, on the tag itself. Okay. And so if I'm standing in line behind you and I'm looking at, say, your bag, the tag on it, or the boarding pass that you're just sort of holding in your hand, there's a good chance that I could get your PNR, and then and probably your last name too, and then I could do whatever. I could cancel your flight if I just wanted to grief you, or I could try and steal your frequent flyer points, or those types of things. Okay, and even if I'm not able to get it, I could also just try and guess it. So 6 characters isn't a particularly long code, and it's worse because it's not like a random 6 characters. Okay, so there's a lot of structure to the code. Like Air Canada's codes always start with the same couple characters or things like that. I don't know if that's exactly what the structure is, but things like the airline is built into it, and maybe the airport and other information. So the amount of it that's actually random is actually quite small, and you could easily try and brute force it just with the computer. Okay, so we bought our ticket. We have our PNR. What's next? So the next thing we're going to do is we're going to check in. Okay, so we might use a kiosk like this. Is that the only option for checking in? So no, you could go to the counter and talk to a human, or you could actually do it from your phone, right? If you don't want to talk to anyone, you could just, or from your computer, you could do an online check-in. Okay, so when you do a check-in, what are you trying to do? What are you trying to get? So a check-in is the output of the check-in process is a boarding pass. And it's also, if you're checking luggage, it will be the tags that go with it. If you go to the counter, probably they're going to do an ID check. Okay, they'll ask for your passport and they'll check it. If you go to one of these kiosks, they might want to scan your passport, but generally they're not going to try to match that passport to your face. Okay, so they don't necessarily know. Sometimes they take a picture of you. It depends. So there's different procedures depending on the airline and the country. But generally, you might type in your passport number or your booking code or something like that in order to just find the database entry that's associated with your flight. But no one's checking whether you're the actual person or not who's doing it, whose name the flight is under. And then if you do it online, there's no ID check, period. Okay. Now, let's say that you're on the no-fly list. So let's go back to the no-fly list. What will happen is by now the airline knows whether you're on the list or not. What they could do is they could email you and say, hey, you can't fly. But normally if someone's on the no-fly list and they're trying to fly, it's often the case that law enforcement wants to talk to that person anyway. They might have a warrant for their arrest or something like that. So what the airline will do is they'll generally let you come to the airport. They'll just give you a sort of benign message that just says, oh, we had a problem with your check-in. You're going to have to do it in person. Okay. Now, if you get that kind of message, by the way, that doesn't mean you're necessarily on the no-fly list. I've got that message before, and I don't know what it was for. It was for something else. Okay. But essentially, you'll get a message like that. And then what they'll do is they'll make you come to the desk, and then they'll say, okay, you're not actually allowed to check in. Okay, so we know details like this because in the news every now and then there's a story about someone who is very clearly not affiliated with crime or terrorism. For example, a child, and the child is somehow on the no-fly list, right? Why are they on the no-fly list? Well, it's because their name matches someone who is, okay? And for a long time, it was just based on name solely, all right? And so this is a case, for example, of a child who I think maybe 2 or 3 times, it's sort of like I see the same newspaper article, but the child keeps getting older and older. And it's like they once again, they tried to fly somewhere and he was, again, like you can see the headline, boy at forefront of no-fly list flight flagged again. And so anyways, now what we have is we do have these traveler identifier numbers or traveler identifier IDs. I forget exactly what they're known. I think they're called like known passenger ID. And so this is for this type of purpose. So now instead of just being a name, you can also be a number. And then if your name matches someone that's on the no-fly list, you'll at least have a unique number. Now these lists, at least in Canada, tend to grow over time. So in Canada, we maintain a list, there's a lot of secrecy around this. So no one knows exactly who's on the list, who's in control. That's also a problem if you're trying to get off the list. Who do you go to get off the list, right? And so generally what you have to do is you have to sue the government and go through a court case in order for it to be addressed. And then there was a story a while ago in The Guardian basically saying that, in addition to the, maintaining our own no-fly list, we also subscribe to a U.S. provided one. And it has 680,000 names, which is a lot. It's a large list. It's probably way larger than the normal list that would be used in Canada. And something like 40% have no recognized terrorist group affiliation. So how did they end up on the list? Well, it turns out that it's really easy to add people's names to the list. So anyone who's in law enforcement, for whatever reason, let's say they're investigating them and they just want to make sure they don't fly somewhere in order to escape, then what they'll do is they can fill out a form and the name gets added. Okay. And so even if a name is added in error, basically there's no way to get it off except for to go through a court process. And because this list is maintained in the U.S., we could ask for names to be withdrawn from the list, but the U.S., they don't have to comply legally. All right. So the outcome of checking in is your boarding pass. So this is an example of what a boarding pass looks like. This is printed out on a piece of paper. It wouldn't necessarily have to be printed out, right? It could be something that's on your phone, QR code, something like that. Okay. Now I've circled a few pieces of information. So I circled the last name and the boarding code. So these are the two types of information that you would need. If you got those two pieces of information, that's why I was saying before, you could change someone's flight or cancel it or steal their frequent flyer miles and things like that. Okay. Then you have details about the flight itself. There's this thing called the boarding group. What's that? Well, that's when you're about to get on the plane. What happens is that the plane, they board in certain order. So they'll call boarding group 1, they'll get on the plane, then they'll call boarding group 2, they'll get on the plane, and then 3, and they'll keep going. Now, let's just say if you could choose, would you rather get on the plane early or would you rather get on the plane at the very end? So generally speaking, it depends. I mean, maybe you don't want to get on the plane early because you want to spend a lot of time in the airport, in the lobby or wherever you are. And so that's fine. But one problem with getting on the plane at the very end is that you might run out of overhead storage for your bags, right? So sometimes people want to get on the plane right away because they want to make sure that they can store their bags somewhere near where they're actually sitting. The worst is if you have to store it sort of behind you, then you have to wait for everyone behind you on the plane to leave before you can walk back and get your bag. So anyways. So there's maybe some competition to try and get like a higher number. Usually if you have privilege or things like that, airline points, or you're part of a loyalty program, one of the things they do, one of the perks is they'll move your boarding group up so you can board the plane sooner. Okay, so basically in general, it's considered a little bit better if you have the option to board as soon as possible. There's another thing called TSA Pre. So this is a U.S. specific thing, but I just included in the example. What's that? So when you line up at security and they're going to check your bags and things like that, there's usually two lines. So there's the normal line that people go through. And then there's a line where it's kind of quicker and there's less scrutiny. And it's for travelers that are trusted. And the reason they're trusted is because they were pre-enrolled. It's usually because they enrolled in some program. So for example, I have a Nexus card. And so that's like a program. I had to go do a security interview and then they gave me the card. And then that entitles me to use these other lines. And when I go through like the border and things like that, I just use a kiosk. In Montreal, you use a kiosk anyway. But anyway, so the procedure was meant to be a little lighter weight. Although now it's a pretty lightweight procedure, I think, for everyone, more or less, in Canada now. But okay. So, but again, this is something you might want. Why not go through the line it's probably shorter. There's less people in line. It moves a little quicker and there's less scrutiny. Why not do that if you can't? Okay. All right. Now, looking at this picture, let me ask you, what if I just want to change this? Let's say I was stuck in boarding group 6, and so I opened my boarding pass up in Photoshop and I changed the 6 to a 1. Or I didn't get TSA pre and I wanted to change it. Could I do that? Okay. First, think about what would stop me. So the first is, well, I'd have to print it out on a weird piece of paper. It might not look like a real boarding pass. Is there any physical security on the paper that a boarding pass is printed on? Not anymore. Okay, so printing passes, people print them at home. They'll email them to you and you can print it at home. Okay, so it's very usual in order to just have a boarding pass that's just printed by yourself. And it might not even be on paper anyways, right? It might just be on your phone. All right, so you can, so there's no physical security around the paper or anything like that. Okay, so if there's no physical security, what about like kind of digital security? Okay, so I see a barcode here. So presumably this information is also encoded in the barcode. And now I'm wondering, is there some sort of cryptography that's used? So the appropriate piece of cryptography to use would be a digital signature. And so this could be signed. Then what would happen is if I change stuff around, it would break the signature. Then when you scan this barcode that would include the signature, then people would notice. Well, it would probably include, first off, if I change it here, it's not going to necessarily change it in the barcode. But if I'm able to change it in the barcode, then the signature is going to break. Okay, so I'll get caught doing it. All right. So what do you think? Do you think this is signed or not? So you might think, yeah, it must be signed. I mean, why not? But I can tell you just by looking at this barcode, just by eyeballing it, that this is not digitally signed. Okay, how do I know? It's because this is like an old school 2D barcode. And I'm not sure exactly how much information this encodes, but I can tell you there's not enough information here for a digital signature. Digital signatures are way bigger than that. And if you put it in barcode format, it would probably take up like almost this entire ticket or this entire boarding pass. Okay, so this is not something that's digitally signed. We also know it because security researchers have looked at it. They've looked at the barcode. They've parsed out it, and they realize that, oh, it's just an encoding of this information. And it's not even in like a complicated obfuscated format. It's just basically just a straight encoding. So if you have a barcode reader, you could read this barcode and you could see exactly like where your name and stuff is encoded, the fields it's encoded in. You could change those names and then generate a new barcode that would match it. Okay. Now, all the information I'm giving you is maybe not as of 2026. When I'm recording this, it might be true of 2000 or earlier. So maybe things have changed. Okay. But anyways, this was true, and I haven't seen anything that would lead me to the contrary to think that this isn't true anymore. Okay. So there's a story of a security researcher named Bruce Schneier, and he took a reporter through the airport, and I'll tell you a few of the other things he did a little later. But one of the things he did is he printed off a fake boarding pass, and he changed the boarding group and he changed the TSA number. You could do things like change your seat, but the problem is that it's not going to match the back-end database. Okay, so when you're sitting in the wrong seat, someone else is going to come and they're also going to have a ticket for the wrong seat, right? Then what United or whoever the airline is, they're going to go and they're going to look up to see who should be sitting in that seat. Okay. But things like this, the boarding group, it's only checked by the person as you're about to board the plane. And this is checked basically on paper. It's checked by TSA, and TSA, they don't talk to United. So they don't know anything about what should be printed on your boarding pass. They're just either looking at the piece of paper or they're looking at what's encoded in the barcode. Okay. And then if you have it on your phone, it's probably in a 2D like QR code as opposed to a barcode, but it's the same kind of idea. And there's no message integrity. Okay. Now, you might ask yourself, well, that seems crazy. Why don't we just digitally sign these things? Put the digital signature in the QR code. Great question. The answer is what we call PKI. Okay. So when you go through the lectures on HTTPS in this course, you'll see that PKI is really hard. How do you figure out whose key is who? So if United is going to sign this boarding pass, right? How do you know that that's United's key that signed it, right? So now you need like sort of root authorities that are going to say. And then the other thing you might think about is like where is that key in order to produce the signature, right? So like, is it in the kiosk? Like the kiosk is printing out these boarding passes. Is it signing it on behalf of United, right? And does that mean the key's in there somewhere? Right? Like if you hacked into that machine, you could steal the signing key and then you could sign boarding passes as if you're United, right? Like it kind of turns into a nightmare just managing the keys and figuring out that these signatures are valid or not based on whether they're signed by the right people or not. And then also thinking about who signs it, when do they sign it, how does that signature get to you printed on your barcode, or sorry, on your boarding pass? You know, how does that whole process work? Okay, what's next? So the next thing we might do is drop off our luggage. So every bag is tagged, so they know who the bag belongs to. It will have the passenger's name and the code, the booking code. You assume responsibility for any bag that's tagged with your name. Okay, so if there's a bag and it ends up tagged with your name, that's your responsibility. You're responsible for what's inside of that bag if it turns out to be problematic. Okay. And then the bags will be inspected. There's two agencies that work side by side, but they actually have different sort of jobs. So in Canada, one's called CATSA and the other's called CBSA. Okay, one of them is concerned with airline security. So the CATSA, they're basically, their primary concern is making sure the flight is safe. Okay, so they're worried about anything in your bag that would make the flight unsafe. Okay, it could be, well, like an explosive. It could be also like products like maybe aerosol cans or toxic things. I don't know. There's a whole list of things that they'll be concerned about. Okay, and then border services. Basically, first off, they only get involved if you're flying from one country to another country. And if you're flying, say I'm flying from Canada to the US, I'll be dealing with the US Border Service. But flying from the US to Canada, I'll be dealing with Canadian Border Service. Okay. And what they're concerned with is, what am I bringing into the country? Okay. And is it legal for me to bring that into the country? So we'll talk about the roles of these two a little bit later, but they're both potentially inspecting your bag. CATSA is definitely inspecting it, and CBSA if you're crossing a border into Canada. Okay. And they have different methods for doing inspection. You can sort of see in the back, there's these conveyor belts, and they might pull it aside and open the lock on the bag and check it, or they'll go through x-rays and things like that. Now, what happens if you lock your bag? So first off, why would you want to lock your bag? So you might want to lock your bag because, well, like I said, you're responsible for anything that's in your bag. So maybe someone slipped something in your bag. You're concerned about it. But it's more like probably theft, right? Like your bag is sort of rolling behind you and you're worried that someone might, be able to open your bag when you're not looking. Or when you get off the airline and you've checked your bag and the bag's going around the conveyor belt and you're working your way from where you landed to the conveyor belt, you don't want people going through your bag. And so people put locks on their bags. But this becomes problematic because TSA, which is the US version, I sort of bounce between CATSA and TSA. They're the same organization, just one's Canada, one's the US. They can't open your bag anymore. Okay, now that's not going to stop them, obviously. So what they'll do is they'll just cut the lock off your bag. All right. Then someone had a great idea. They said, hey, we should have special locks. Okay. We'll sell them in every store. So every store that you go to where you can buy luggage, they're going to have these special TSA certified locks. And these locks will have a master key, and the master key will be controlled by TSA. So TSA agents will have this master key, and then you'll have your own unique key as well. Okay. And so when you lock your bag, other people may have these certified locks, but they'll have a different key than yours. So their key's not going to unlock your lock. But the TSA agent will have a key that unlocks them all, a master key. All right. And so you can still buy them. So you can still go and buy these locks. Okay. Now, what happens if you have one TSA agent once that loses possession of their master key? Now you have a master key that can unlock every single one of these locks. So these locks are basically useless. If there's a thief that, first off, the thief can always just steal your bag, right? Take them home, or they could cut the lock as well. But anyways, now they have the option of having a master key that unlocks all of these locks. Okay. You can 3D print it and you can download it. You can download it and 3D print it, and you don't have to know someone in particular in order to get one of these keys. And even if a TSA agent, there's 50,000 of them roughly, and so it just takes one of them to leak it, right? But even if you couldn't get a TSA agent to leak it, there's also this like thing about keys and locks, which is because a master key has to unlock every lock, and your individual key has to unlock the same lock, there has to be like a connection between the two. Like there's something about the pattern that's on the master key that's common to the pattern that's on your individual key. Otherwise, the two keys wouldn't unlock the lock. So it turns out that at least for simple locks, if you just bought like say 10 or 100, I'm not sure how many you needed of these locks, you would get like 10 or 100 different keys. But what you could do is you could sort of, you could look at every key and see what they have in common, and then you could derive what the master key must be based on seeing lots of examples of individual keys themselves. Okay, so anyway, this basically this this master key leaked. Now you can download it and 3D print it, and so basically all these locks are useless. This is just another example of that general policy, which is the thing here is like if you give a secret to 50,000 people and it just takes one person to leak it, it's probably going to leak. Okay, this was just a news article I noticed, and they were saying that the number of people with top security clearance is about 1.25 million. Okay, now top security, this has nothing to do with airlines. This is just another example, but this is like secret documents, government documents, and things like that. Right. And so it just takes one person out of, millions of people to start leaking this stuff. And that's why you have lots of leaks and whistleblowers and things like that. And also, government secrets, being sold to other governments and all of that type of stuff. So it's a bad policy in general. If a secret, you can't have a secret shared amongst thousands of people. Another thing that happens is that your bags are usually physically isolated from where you are. So you couldn't access your bag mid-flight even if you wanted to do it. I understand that part of this is climate. So like this is not necessarily pressurized or climatized. So your bags, it's just a storage area. But it can also be a sort of safety thing where someone can't go and get something out of their bag and then bring it back on the flight, something that would harm the safety of the flight itself. Okay, what's next? So you might think we're ready to go through security now, but we're not quite ready. So usually what happens is when you stand at the outside line, waiting to go into security, there's someone that scans your boarding pass. This person works for CATSA. In Canada, they're not going to check your ID. They're just going to check your boarding pass. Okay, so they don't know that you are the person. You still haven't shown your ID to anyone. If you checked in online, you've made it this far through the airport and you've never shown your passport to anybody. And that's the same thing here. So they're just going to check your ID. Your boarding pass. In the US, sometimes they check your ID as well. So we can think about that a little later. Why do they do this? Why is there this sort of scan before you even get into the line? So the main story is just logistics. It's not necessarily a security thing. So like they just want to be sure where you are. So normally they're going to scan it at the start of the line. They'll scan it again when you get, through the line and you're actually going through security. This lets them see, for example, when you entered the security line. Sometimes the security lines are really long. right? And you might miss your flight because the security line is too long. And so this lets them to see like sort of, okay, there is a passenger, the airplane's ready to take off, but they're missing a couple passengers, and they can see that they entered the security line. Maybe they were rushing last minute, and so like it's just going to take off because they entered it too late. But they might see that, oh no, they've been in that line for a long time. Maybe we need to send someone to find them and try and get them through that line faster, that type of thing. Okay, so it's just sort of about logistics. And then it turned out, no one thought that this was happening, but there was a leak to the press. And it turns out that these agents are more than just logistical people, at least in certain jurisdictions in the US. They actually had special training, and their training was for a security purpose. It was to try and identify terrorists or terrorism. And so there was this procedure called SPOT, and it was a kind of check mark based system. And because it leaked, we can actually look at it. So I'll show you the document itself. And what it would do is what the agents would do is they were looking for behavioral characteristics, and they would assign you points. And if you got too many points, they would refer you to law enforcement. I'm going to try and make it a little bigger. It doesn't seem to want to let me zoom in much further than this. Okay, so you might be a little small here, but I'll just read you. So, for example, there's a list of things that would get you 1 point. Okay, so if you're sweating a lot, if it looks like you recently shaved off your beard, if you're Adam's apple, which usually in males is something in your neck, if it's kind of like jumping around, if you have strong body odor, sweaty palms, that type of thing, this is going to get you 1 point. There's fear factors. So if you have a cold, penetrating stare, if you're looking around a lot and paying a lot of attention to like where security or law enforcement agents, officers, LEO, law enforcement officers, that will get you 2 points. And then 3 points if you're actively trying to deceive someone. So if you, for example, are obviously in a disguise or something like that, then you get 3 points. Okay. And then you can get points taken off as well too. So if you're traveling with a family, if you're married, but if you read the fine print, it's married and over 55 years old, based on me looking at you trying to figure out how old you are, or just generally people that are old. So it says female over 55 and male over 65, then they'll deduct 1 point. If you get 0 to 3 points, that's fine. So you can have some of these characteristics and nothing will happen. But if you get at least 4 of them across all the things, then what they'll do is they'll refer you to secondary screening. So secondary screening means that they'll pull you aside, usually into a room, and they might manually search you. They'll talk to you and things like that. And then if you get 6 or more, they'll not only pull you into secondary screening, but they're going to notify law enforcement officers, LEO. So they're going to remember these people. They look like police. Maybe they have guns and uniforms, but the TSA are not police. But what they will do is they'll refer you to the police. And police, usually for any major airport, there's going to be like a police presence in that airport. Okay. Then there's other things, again, based on a point system. So there's unusual items that you might be traveling with, blueprints, photographs of high-profile targets, rope, duct tape, loose batteries, that type of stuff, electronic components, military stuff, training manuals. Okay, so what's sort of the point of this? So there was a hearing after this program was discovered, and I forget if it was in the U.S. Congress or Senate or something. And so here's a psychologist who was testifying, who said humans do barely better than 50% chance. So think of a coin toss in trying to guess whether someone's being deceptive or not. So if you flip a coin or you ask someone whether somebody's being deceptive, you have a 50-50 chance of guessing in either cases. There's sort of this myth that some people are better at reading people than others, but the science shows that there's no actual variation. And if you're an expert and you have a lot of training, you aren't going to get better either. So a program like this, where you're trying to get TSA agents to get a lot of training on trying to detect deceptive behavior, we don't expect that it's actually going to help, and that you're going to end up being more reliable than just a coin toss in terms of deciding whether someone has deception or not. There's a reason for this is that there aren't any actual sort of biological cues to deception. And you make a lot of mistakes too. So there's a lot of reasons why you're going through an airport, you're stressed, you're nervous, and it's not necessarily because you're deceiving or telling lies. We can also look at the program itself and just ask, how successful was it? So it was designed to be counterterrorism. That was the goal of it. And so they ran it for 5 weeks in a trial. And I forget what the numbers of people that went through it would be. You can do the reverse math to get the number out, but 4% of that number is 429. And these are the number of people that were referred because of this program to getting secondary screening. Okay. But then at the end of secondary screening, only 47 were referred to law enforcement. So law enforcement, came in, conducted an interview and investigation, and most of these people were not arrested. Only 16 were. Of all the arrests, 14 were arrested for some immigration reasons. One was because they were intoxicated. One, I guess, possession of drugs. And 0 terrorists were found. Okay, so for a counterterrorism program that costs almost $1 billion to roll out and do all the training and things like that, at least in this one trial, it caught 0 terrorists. Okay, so this was a very controversial program. People thought that there a lot of critics also thought that it was actually really, people were saying it was counterterrorism and they were using the sort of terrorist budget in order to pay for it, but it was really more about controlling immigration and trying to find undocumented people in the United States as well. And you can go back to the criteria too and go through and decide if they're, really objective criteria, or some of them are sort of racially tinged as well. But I'll leave that as an exercise for you to look at. Okay, finally, we're ready to go through security itself. Okay, so when you go through security, it's being run by CATSA or TSA if you're in the US. Again, we're not checking IDs. Okay, they will scan your boarding pass. Logistical reasons, just to make sure that you're through security. So if the flight is looking for you and they see that, you went through security 30 minutes ago, they know that you had a lot of time to get to the flight. And if you're not there, they're they don't know what happened to you necessarily, but they know it's not the airport's fault, right? It's something happened to you. And so when you go through security, there's metal detectors. First off, so your bags are going to be separated from yourself. Okay, so your bags will go through one kind of machine and you'll go through a different kind of machine. Why is that? Why don't the bags just go through with you? Well, this machine is very invasive. It's going to use X-ray technology. And for reasons of concerns about cancer, we don't want to put humans through those kinds of X-rays, especially frequently. And so what we do is we put them through a much lesser invasive thing, which is a metal detector. Okay. Or there is a kind of X-ray, but it's a lighter weight. So it's meant to just scan basically from your clothes to the surface of your skin, and the X-rays are not supposed to penetrate your skin. And so that's the machine where you go in, you sort of hold your hand up in the air, and then there's this like scanner thing that kind of whirls around you. Okay. As a result of this basically the alarm will go off if it detects metal. Okay. And there are people who, for medical reasons or something like that, they may have metal implants or things like that. They're going to set off this kind of alarm. This is more about scanning what's on the outside of your skin. And the results of this will be an image, and the image will be seen by someone who, for privacy reasons, is supposed to be in a completely separate room. So they're not supposed to be able to see you as a person and also look at the scan that's a result of this, because that scan is essentially like an image of your naked body. Now, by the way, you can opt out of this. If you don't want this, you can opt out, and then they'll do a physical pat down, which you may also get as a secondary screening. So secondary screening often involves a physical pat down. It may also involve like questioning and things like that as well. So here you're physically checking for anything that might be on a person. And your bags and things like that, they can open up. So you'll know that when it goes through the x-ray, there's usually kind of like two conveyor belts. There's one that spills it out where you can grab it, and there's another one that puts it behind usually a screen or something like that so you can't grab it, and then a TSA agent will open it up, and if you forgot to take something out of your bag that you're supposed to or whatever, they'll be able to find that. A few other things that are used, sometimes dogs are used. So I once was in an airplane or I was at the airport, and they made us take our bags and we all stood in a big circle, and no one was really sure what was going on. And then they brought a dog out, and the dog kind of ran around in the circle twice, and then it went back. And then we all thought it was like just a sort of like a secondary screening. But they were like, no, you're good to go. Like, you don't have to go through the metal detectors anymore. You can just go directly to your flight. And so the dog in this case, we think of dogs usually maybe as like drug sniffing dogs. So drugs are a concern of border services, but they're not a concern of TSA. So TSA is about airport security. So they're more concerned with explosives. So what these dogs are doing is they have very sensitive sense of smell. And so they're trying to smell chemicals that would be used in either the creation or the handling of explosive materials. You might also, if you were to handle explosive materials, get chemical residues on your hands or on your clothing. And so this is another type of secondary screening. Usually after you go through the metal detector, they'll pull people aside and they'll swab you. And then they have a machine. She takes maybe about 30 seconds, and it will try and detect if there's any chemical traces on the swab of explosive materials. Okay, this is the list of stuff that you can not take on to a plane. So guns, firearms, that type of thing, stun guns, sharp objects, knives, blunt objects, explosives, acids, things like that. And then the one that we're all familiar with is the liquids. So you can only take, in Canada, up to 100 milliliters. And it's a lesser known rule, but all of your 100 milliliter toiletries or whatever, they all have to be able to fit into a 1 liter sealed plastic bag. Okay, so if you have more than 10 of these things, it's not going to fit. And usually probably a lot less of them, just because of the size of the bottles and things like that, is going to make them not fit. Okay. Now, why is that the case? Why is there a limit on how much liquid? Why can't you bring a bottle of water onto a plane? Right. So the answer is that, well, there's explosives, and explosives can be made out of liquid, and they're pretty powerful. And they're also kind of harder to detect, especially if they're in, say, a glass jar or something like that. You might not get chemical traces on the outside. A dog might not be able to smell it, and it's going to look just like a clear liquid. And so it's going to be indistinguishable from some other liquid that you might be carrying. And so the main constraint here is to just try and limit the amount of liquids that someone can bring on. Okay. Now, is it truly limited? Is this a hard limit on the amount of liquid that you can bring on? The answer is no. There's actually exemptions. So there are ways in which you can bring a lot more than 100 milliliters onto a flight. So if you ever travel with a baby, you'll know that breast milk or formula is something that you can bring as much of it as you want. Okay, so you can bring liters and liters and liters of it. It's something that you can't just go and buy, say, breast milk at in an airport lobby. And so you have to bring, your baby has to eat, and so you have to bring whatever you're able to bring. And even when you fly somewhere and you land, you might not have access. And so it's allowed to bring as much as you want. Okay, so if you're a terrorist and you want to get your liquid explosive onto a plane, what are you going to disguise it at? Well, you're going to disguise it as something that there's no exemption, or there's an exemption for, that there's no cap on it. This isn't the only exemption. The second one's not really written down the same way it is clear, but there tends to be an exemption for contact lens fluid or saline solution. Okay. And so back to Bruce Schneier, remember he was someone who carried a journalist. This article is great, by the way. You should read this. He took a journalist kind of through the whole airport security and did a bunch of stuff that aren't in the slides. I pulled out some of the best bits. But one thing he did is he created fake boarding passes for them so that they could board early and get TSA pre-screening. And then when they were in the TSA pre-check faster screening, but when they were in the faster screening, he had in his bag 2 bottles labeled saline solution. So my understanding from the article, it sort of painted the picture in my mind of like not like an official brand name bottle, but like just like a bottle with like masking tape and like in Sharpie marker it says saline solution or something like that. But it was way above the limit, 24 ounces in total. And an officer did pull the bottles, I guess, out of the bag. And he was like, oh, they're saline solution. It's, for my contact lenses, it's fine. We're allowed to bring, more than the limit. And the officer said, okay, that's fine. You're right. You are allowed to bring it. But just as a curiosity, why do you have 2 bottles? And Bruce Schneier said, because I have 2 eyes. And he was allowed to keep the bottles. Okay, another thing, there's some restrictions around our laptops. You probably know you have to pull them out of your bag. Why? So there's 2 reasons I've heard. One is that the X-ray just can't see through them, so they can't see what's on the other side. And there was a weird scenario too. I didn't realize this, but I had a textbook in my bag, and it got pulled aside. It went down the other belt off the conveyor when it came out of the X-ray. And they said, oh, it's because there's a textbook. And so it was, I guess, obstructing the X-ray from seeing through it. The other thing is it could look like some of the components that you might see in an explosive. And so having it out of your bag also allows people to, it allows the agents to test whether it's actually a computer or not. Although they don't have a very sophisticated test, what they'll do is they'll just try and power it on. If it powers on, then they consider it a computer. Now, maybe they would look, if there was some indication, they could look as deep as they wanted into whether it's a computer or not. But if you wanted to have a laptop that just turned on, you wouldn't need the full circuitry of a laptop, right? You could have some very small, like Arduino Trip or something like that, Raspberry Pi or something like that inside of it. And then you'd have a lot of a lot of the cavity of the computer would be left over for whatever you want to put in. There was a big deal about taking our shoes off when we flew. This is now, I think, lifted in most countries, including Canada. But for decades, we'd always have to take our shoes off, put it in the basket. Why is this? Well, as Bruce Schneier says, we defend against what the terrorists did last week. Although in this case, it was like maybe the last decade. But what was it that they were doing? Well, there was someone who put a bomb in their shoe. They tried to ignite it when they were on the flight. Someone that was sitting beside it thought it was unusual, and so that person sort of tackled them and restrained them. They took the shoes off, and then law enforcement came, and then law enforcement investigated the shoes, and it turned out that there was an explosive in the shoes. And so now what we do is we take our shoes off. They go through the X-ray so that the X-ray can take a closer look and make sure that there's nothing in it. Or if there was an explosive in it, then it would show up on the X-ray. Now, Bruce Schneier is sort of critical of a lot of the security stuff. He calls it security theater. His argument is that because a terrorist put an explosive in a shoe and now every shoe's being inspected, there's no way that a terrorist is going to put a bomb in a shoe again, right? They're going to put a bomb somewhere else. And so why do we invest so much time with everyone taking their shoes off, when we should spend the time trying to do something more meaningful about trying to prevent terrorist attacks. And so the idea of security theater is just that, you pick up the newspaper, you read about these shoe bombs, you're really concerned about it, you don't want to fly, but now everyone's taking their shoes off and it's going through the X-ray, and so you feel good again. And so as a result, you're happy flying again. So it's more, it's not true security. It's not really geared to trying to reduce the amount of terrorism. It's more like security for security's sake, for theatrical reasons, to make everyone sort of placated and feel like there's a lot of security going on, and then be more comfortable flying. All right, so we make it through security. What's next? Okay, so you might not be expecting this. I snuck it in here. So in Canada, if I fly to the US, we actually do customs before we get on the plane. So there's US customs in the Montreal airport. That's usually not the case. Usually you're going to do customs at the very end. But for fun, we'll just throw it in ahead of time. So for customs, you're going to, first off, you're going to show your passport, your ID. They don't necessarily want to see your boarding flight details or your boarding pass. But a lot of times they do. So they also have a computer, and it's not clear exactly what information they have on the computer. But they're the first to sort of connect all of these pieces together. But you only go through boarding or through customs, rather, if you are flying internationally. So if you're going from country to country. If you're flying domestically within a country, then you're not going to do this. Okay, so this process wouldn't happen. Terrorism is a concern for border services, but that's more like what the TSA or the CATSA are looking for. Border services are more concerned about, like, what are you bringing into the country? So there's things that are prohibited, and there's things that are allowed, but you have to declare them, and you might have to pay duty on them. So restrictions apply to a large amount of cash, so more than $10,000. Controlled substances, so that would include drugs, weapons, and food items as well. So there's a lot of cases of you might be traveling in a country and you buy some cheese or something and you want to bring it back, but there might be insects or bacterias or things like that that are in that country. They're invasive in Canada and they're not yet in Canada. And so Canada wants to control making sure that that type of stuff, or there's no risk of that kind of thing coming into the country. There's a great TV show, fun TV show. It's a reality TV show. It's called Border Security. It's Canadian, and it's real life cases of border services doing their job. And so it usually follows like 3 different cases where they have to get involved. And you see everything. So you see some people with a lot of cash. You see some people with food. It's TV, so they know that there's cameras there and things like that. And obviously, the editors are choosing the stories that make for the best television. But at the same time, it is real life, and the people that are being investigated aren't necessarily consenting to be on TV. Sometimes they blur their faces. Sometimes they sign the release to not do it. But it is a real TV. And so one thing I noticed watching the show is that if you're ever detained, you have very limited rights. I think you probably have more rights if you're detained by police than you do in this situation. You're sort of between countries in a sense. And the border services will do what they have to try and figure out what's going on. So a lot of the cases involve people who are crossing the border under they're claiming one set of circumstances, like they're just coming here to visit and they're going to leave in a week. And then the reality is a different set of circumstances, like they're coming here permanently, or they're moving here, or they're taking a job. They're going to be here. They're going to make money, and all that stuff is fine. You can do all of that stuff, but it requires certain visas that that the travelers didn't get. And so what border services will do is they'll take their phone away, and you're legally compelled to give your password, and they'll unlock the phone. They'll take it into another room, and they'll just start going through it. They'll read emails, they'll read phone messages, they'll see who called you, and then they'll start calling people. And so they'll call someone and say, okay, I have this person here, and they, can you tell me why they're coming to Canada? And the person might say, oh yeah, I hired them, they're going to work on the farm for 2 weeks or whatever, and and so that's like the investigative powers are very, like, they'll do whatever it takes to try and figure things out. Okay, now finally ready to board the flight. Okay, so when I board the flight, I'm going to deal with the airline. So the airline is the person that I'm dealing with, not the TSA, not the border services. They're finally going to check my ID, so I'm going to show my passport, or if I'm flying domestically, I'll just show my driver's license or some sort of photo ID. The boarding pass, they have a back-end database. They know that I have booked the flight. They know my seat number. They know all of that type of stuff. They'll scan it. The database will basically say, yeah, everything's right. The person, this is the name on the ticket, and then they'll check the passport and make sure that it matches. I guess you could get denied if you maybe forgot your ID. It's possible if you're flying domestically that you made it all the way to the gate without realizing you left your passport at home. And it's also possible that you are denied, I don't know, for something about you yourself or the state that you're in. So like if you're intoxicated, for example, that's the kind of thing that could get you denied. But generally, as long as, you have your proper ID, you should be allowed on the flight because basically everything else has been checked out for you. Now, some countries like the US previously, they wouldn't check ID on domestic flights. They would on international, but the airline wouldn't check it on domestic flights. They had an earlier step where before you got to security, they would get checked. Okay. So anyways, we'll talk about the consequences of that because the consequences are important. So it led to a kind of loophole. So this is what would happen. When you check in, you book your flight, you give them your name. They have all the information to make your boarding pass, whether you have it or not. And this is where they check whether you're on the no-fly list. Then in the US, so this is different than in Canada, there is an ID check. Okay, the ID check is done by TSA and it's done before you get into security. So where they were doing that spot program out at the start of the security line, they would also have a booth set up and they would check your passport and they would check your boarding pass. The problem is that TSA is not the airlines. So they don't know anything about whether your boarding pass is correct or not. And we said that the boarding pass itself has no security. There's no message integrity or physical security on it. So the boarding pass that you show them doesn't mean anything. It doesn't convince them of anything. Okay, they're mainly, they know what a real passport looks like and they're doing the ID check. They can check the name matches what's on the boarding pass. But if this boarding pass was completely fabricated, because they're not the airlines and they don't have access, it seems, to the airlines' back-end databases, they don't know whether this flight is actually real or not. Then what would happen is when you boarded the flight, in an ideal world, they're going to check all three of these things. Okay, so the airline knows in their back-end database whether you can fly or not. You probably wouldn't get the boarding pass in the first place if you were on the list. They have a copy of all your details, and then they're going to check those details against the ID itself. Now, the problem that I was saying is that for domestic flights in the US, until this was pointed out, until what I'm going to show you was pointed out, they wouldn't check the ID when you were about to board the flight. Okay, so because they reasoned that it was already being checked by TSA, so there was no need to check it again a second time. Okay, so if you look at this and you think about, is there a loophole here? Right? And by a loophole, what I mean very specifically is there a way I can get on this flight, I can satisfy all the checks and actually be on the no-fly list? So there's no way I should be able to get on the flight, right? But for some reason, I'm able to get it on it, okay? And so it turns out there is an attack here. The attack is, when you look at the overlapping diagrams here, the assumption you're making is that the boarding pass that's being shown here is the same as the boarding pass that's being shown here, but you can't assume that, okay? And a lot of attacks have to do with what we call equivocation. Equivocation, this is across cybersecurity. So equivocation is basically just saying one thing to one person and a different thing to a different person. And if those two people never talk, they don't realize that you're telling them different things. Okay, so the idea here is that you go book a flight in someone else's name who's not on the no-fly list. So as far as the airline's concerned, you're all good. Okay, the only problem you have is you can't show them your passport because your passport doesn't match their ID. Okay, but the airline is not checking your passport. All right, they never check it. And the person that does check it doesn't have a way of checking the boarding pass because they don't know whether everything on a boarding pass can be faked. Okay, and they don't have access to the back-end database. So what you can do is you can make a boarding pass that's a copy of your real boarding pass, but you change it to your real name. Okay, so you have your real name here that matches your real identifier. The only problem here is that you aren't registered for the flight. There's nobody on this flight under your name. The person that's on this flight is someone else's name. Okay, but because TSA don't have access to the backend database, they can't check that information. Okay, so this was pointed out by a researcher. His name was Chris Soghoian, and then he got his door kicked on in the middle of the night by the FBI. They took all his computers and things like that. He did nothing wrong. There was no charges. He got everything back, but they weren't happy with him, I guess, for pointing out this flaw. But he also pointed out the flaw that boarding passes don't have any signatures or anything on it. And he actually had a website where you could create a fake boarding pass that had all the right, it had the QR code and it was encoded correctly and things like that for whatever information you wanted to put on it. And then a little bit later, TSA announced that, oh, by the way, we're changing our policy. Now we're going to show ID, even if it's a domestic flight. You have to show your ID when you board the flight itself, as presumably a direct response to this policy loophole that was pointed out. Okay, so that's it for airport security. Now I just want to focus a bit on sort of high-level lessons that we can learn from all the examples that we saw. So one challenge that the airport example illustrates is that in this case you had an overall security goal, but there was no one organization that was responsible for it. So the enforcement of this policy that someone on the no-fly list should not be able to fly, it's kind of split across different organizations. They're not necessarily talking to each other, and they have their own internal policies, and they might not be compatible. So anytime you have different people with different policies and not necessarily like sometimes siloed communication between them, then you can have problems. Or it's at least it's a more difficult challenge to solve policy problems like that and make sure that there are no loopholes. Another thing that the researchers of the paper pointed out is they said that this is sort of directed at academics. So the quote is, technological sophistication and research novelty are negatively correlated with security impacts on users. What they mean is that there's a bunch of things that really impact your life. SIM swapping is one. Like lots and lots of victims of SIM swapping. Okay. There's other security things, like, for example, SIM swapping, it's a big impact because of two-factor authentication. Okay. So it's tied to authentication. Now, you could pick another topic in authentication and say, I'm going to study the cryptography that's used to hash and salt passwords when they're stored in a database. And I'm going to work out all the cryptographic details, and I'm going to write a security proof that's 40 pages long that this protocol works exactly correctly. And that's probably going to be low impact on users, but that's going to be the kind of thing that it's easy to publish. It's very technical. It looks great, but it's not necessarily the high impact kind of stuff. Okay. And so they feel that policies fall into this example of things that are really high impact. A lot of people are affected by policies, and there isn't a lot of attention, not enough attention that's being paid to it. Now, why isn't enough attention being paid? Well, it's part of the reason probably is that it's not easy to solve. So like, how do you go about even solving these policy loopholes and finding them? So one thing you could do is you could do external audits. So you could have people, try to come in and audit whether the policy is working or not. So the researchers, they themselves sort of did this indirectly by doing the SIM swapping experiment. That took them hundreds of hours. They had to get ethics clearance from their university and things like that. Another thing you could do is you could have companies that have policies. They could offer a bug bounty, similar to like if you find vulnerability in their software, you can disclose it responsibly to them, and they'll often pay you for it. So they could offer to pay for this type of thing. You could use lawmakers, people in Congress or House of Commons in Canada, they could try to say, okay, we figure out that there's these loopholes, let's close them. And we're going to force people to close them using regulation. So there was a lot of changes made to how SIM swapping procedures worked with telecoms because it was so vulnerable. And so that was, the FCC is a division of the U.S. government that spearheaded that. But there's other places where, regulation could kick in on the airline side or on the USPS side, those examples that we saw earlier. You could imagine cases like that. Another thing you could do to bring attention to policy loopholes is just, do a lot of press about it. So the @Matt example, which you'll see in the social engineering unit of this course, that was a front page cover of Wired magazine article about what he went through. And did Amazon change their policy after that article? You bet they did, right? Probably before it was even published. Probably Wired approached them for comment, told them what the article was about, and they changed it right away. Another thing that looks promising is something called formal methods. So the idea here is that you can't really like we have all these tools for code. If there's vulnerability in code, like static analysis and dynamic analysis and things like that, could we take that and could we run those kinds of tools on policies? Well, we can't out of the box because policies aren't really written down. But what if we did? What if we wrote them down and we wrote them down in a way that a computer could understand them? So it could be as code or formal logic or mathematical expressions. There's different ways of formulating it. Then what you can do is you can ask the computer to basically go through it and try and make sure that that there's no vulnerabilities or there's no loopholes. So basically what you do is you would say, this should never happen. Someone on the no-fly list should never be able to get on a flight. Here's all the checks that are done. I want you to think through every possible scenario that you can think of and see whether you can ever find a scenario where someone that's on the no-fly list steps onto a plane. Okay. And the computer has a bunch of algorithms for sort of efficiently doing it. At the end of the day, if it doesn't find anything, it's not a guarantee that there wasn't a vulnerability. But it has a bunch of tricks that it can do, and it can usually find things that you might have missed. So later, right after this, we're going to talk about browser policies. And so this was something that some researchers did for browser policies. They took what's called the same origin policy. You're going to learn about that in about an hour or so. And what they did is they modeled it formally. They gave it to a computer, and they did it based on the way that Firefox implemented it. And the computer found all sorts of, they said, the basic constraint was if you're running JavaScript on a website, it's from origin A, and you have a resource that's on the website from origin B, A shouldn't be able to see B or manipulate it or have any, should be isolated from it. Is there any conditions under which this isn't true? And the computer, lo and behold, found a bunch of things. And then they were able to fix the browser and strengthen it and harden it against those attacks. Now, there's always the risk that when you model it, when you turn the policy into code, you do it wrong. You either make mistakes or you miss things. And so the coded version of the policy is fine. There's no vulnerabilities in it. But the real policy is a little different than what was coded up. And the problems are in the real policy itself. It's also a pretty expensive process, and you can't easily, you can't spend a lot of time doing it for one kind of policy and then save a bunch of time when you want to do it for policies 2, 3, 4, or 5. Usually you have to do them all kind of from scratch. At least in terms of the turning the policy into code. The thing that you can reuse is the reasoner that will check whether the policies are correct or not. So anyway, this is one research future direction. It's a great topic if you're a researcher or if you're looking for a class project or something like that, thinking about how you might use these things. But right now, this is something that's more futuristic. It's not something that's being undertaken now. As of right now, we don't really have great methods for looking at policies. It's a problem. I was happy to raise that problem in this course. And now what we're going to do is we're going to turn our attention to two other kinds of policies that relate to browsers. All right, so in today's lecture, we'll continue talking about policies. In this case, we're going to shift gears a bit and we're going to talk about technical policies. So the two policies we'll talk about, they stem from web browsers. Web browsers were something, so as far as I recall, the internet was created maybe in the 1970s. The early days of the internet focused on protocols like email. There wasn't really this notion of websites, and you would go and browse the web and go to different people's websites. As a result, there also weren't tools or software programs for allowing you to browse the web until about the 1990s. So that's when web browsers came out. It's when this notion of the World Wide Web came out. There was also some more like kind of walled garden approaches where you would subscribe, to an internet service provider, and then you could access websites that were hosted within that. But in terms of the open, internet, it didn't really come along until the 90s. The first major browser to break through to the mainstream was Netscape Navigator. It came in 1994. Microsoft introduced Internet Explorer, put it into all the copies of Windows that were being sold, and that came in 95. Now today we have things like Chrome, Edge is Internet Explorer, Safari from Apple, Firefox, Opera, and so there's other browsers as well. So going back to Netscape, what Netscape did is very early on, so in the first versions of Netscape, they had to work out a lot of, they made a lot of decisions about how websites should behave and how browsers should behave, and they worked out different policies, which is the focus of the lecture. And so they worked out different policies for how the browser should handle certain types of circumstances. And no one had really thought these things through before, because there wasn't really a lot of browsers before, and the internet was just like in the very, very early days. Once they fixed these policies, then when new browsers came along, they would just sort of copy them. And so there have definitely been tweaks along the way, but for a large part, the decisions that Netscape made in 94, 95 still shape, the way that browsers work today to a large extent. So what we're going to do is we're going to look at two policies. Today, we're going to look at how browsers handle what are called cookies, and I'll explain what a cookie is as we go through it. And then next class, we'll talk about a different policy called the same origin policy, and it governs how a browser will handle active web content. So scripting in particular is the most important today, so like JavaScript and things like that. Okay, so we've seen this slide before when we talked about HTTPS, but we'll go over it again. So the content, when you download a website, let's say you go and you visit a website, you're getting a bunch of information from the web server. So your browser is receiving a bunch of information from it. And the first thing the browser is going to do is it's going to split what it's going to show to you, like what is part of the content of the website itself, and what is just information for the browser to know about the website itself that won't necessarily get displayed to the user. If you want to use an analogy of an envelope, there's a bunch of stuff that's inside the envelope, so that's like the content of the website, and then there's stuff that's written on the outside of the envelope. So cookies, which we'll talk about today, cookies are on the outside of the envelope. So they're not something that's displayed to the user. It's not part of the content of the website itself. It's something that's just getting sort of sent along with the website. And so it actually is added both when you request a website and also when you receive the website back. There's other things like, browsers will talk about, like what version of which browser it is. Like this is Safari, it's this version, maybe it's running on this operating system, this is the screen resolution, here are some fonts that I have installed, or the website might ask for the fonts that are installed and things like that. So there's a bunch of other stuff that goes back and forth. That's just part of the communication between the browser and the website. Again, if we go back earlier in the course, we talked about Tor, and we talked about de-anonymizing people who are visiting your website if you're a web server. And you automatically know their IP address, but with things like Tor, VPNs, or proxies, it's going to hide that information. Another way to track users is to try and figure out if their configuration looks like the configuration of any of your other users, and if it's somehow unique, like it has certain fonts that like that exact combination. You don't have any other user with that exact combination that's maybe running that version of, say, Safari, from a computer as opposed to a phone, that type of thing. So that's other stuff that gets passed back and forth in this meta content. Okay, then you have the content itself. So this is the resources on the website. So usually the base piece of content would be an HTML file that's going to define the website. But the HTML file, either inside of it or through links, it's going to pull in other resources. So it could be other HTML, it could be JavaScript, it could be some sort of scripting file, it could be video, it could be audio, it could be pictures. So all of these things come down. And then we also like to distinguish between passive and active content. So passive content is not code, it's just something that's going to get displayed. So the HTML itself is passive. The images, audio, video, they're all considered passive content. And then active content is things that is running. It's code that's being run. So JavaScript is the big one. XML HTTP requests is a little different. It's sort of it's the way that JavaScript requests that a website come down. So once JavaScript's running, it can also load resources itself. And the way it loads resources is through this protocol. Next class, when we talk about browser policies concerning scripting, we'll see all of these things again. CSS files is another one. It's a style file. So normally you would use it to say, you might install it, like say you have a website and you have 100 different subpages, but you want them to all look the same, like have the same menu options and have the same border and background and color scheme and fonts and things like that. So that's where you would put it in the CSS file. CSS files should arguably be passive content because it's not code. It's just a specification or a markup of what you want the layout to look like. The problem is that the CSS sort of format, it kind of slipped over the years, and developers wanted more and more powerful features in CSS, so they could do more just with the CSS file. And at a certain point, it kind of crossed the threshold where now it's dangerous. There's potentially attacks that could be conducted using these files, and so now we consider it active content, even though most CSS files themselves would not involve anything that looks like active content. Okay, what are the security goals in terms of a browser itself? So if we go back to Stride, what the browser is doing is it's essentially trying to provide two properties. So the first property is what you see is what was sent. So I'm looking at a website, it was given to me by google.com, and bit for bit what I'm looking at on my browser was bit for bit what the server sent and wanted me to see. Okay, so there was no tampering that sort of changed the content of the website or that type of thing. Okay, the other thing we care about is privacy. So what we exchange with one particular website or domain name shouldn't be seen by other people. Okay, so it could be other people that are on the wire that are listening to our content, so that would be like HTTPS that would prevent that. But you can also start thinking about, well, what happens if, let's say you load a website and, you're visiting one particular website, but there's content being loaded from a bunch of different websites, and it's all getting weaved together on the same page. right? What about those other websites? Do they know what you're doing on the primary website that you're visiting? Can they sort of trace you or track you? If you type information into that website, do they all get to see that, or is it just the primary website? So like, how do you isolate content when it gets weaved together from multiple sources? So things like that. So that's sort of privacy within a particular website that you're looking at. And then you can also think about privacy from the perspective of, let's say I visit the website today, I come back tomorrow, I didn't log in, maybe I changed my IP address, maybe I'm using Tor or something like that. Does the website know I'm the same person? It might not know who I am, but does it know I'm the same person or not? Okay, and so that particular privacy or information disclosure property is more relevant to what we'll talk about today. Okay, now let's consider just an example to warm up to the idea of cookies. So I go to my email client, say I use webmail, I use Gmail. So I go to Gmail, it asks me to log in, that's fine. I put my username, I put my password in, I log in, and it shows me my inbox. Okay, so I have 20 messages sitting there, and now I want to read the first message. Okay, so I click on the first message. Now we all know the answer to this question, but think about it for a second. Do I have to log in and give my password again to click on that first message and see that first message, right? Gmail knew who I was. It showed me my inbox because I just put my password in, right? Now I'm clicking on the first message, so don't I need to send my password again so that Gmail knows I'm the same person, or I'm allowed to look at that message? Okay, so we all know that you just click on it and you don't have to log in again. Okay, but it's worth thinking about why. How does Gmail know that I'm the same person? Because technically this is a second request. I did the first request, which was give me my inbox. I go away. Maybe I go away for a while. Maybe I load my inbox. Maybe I'm like taking public transit, and I load my inbox, and then I switch from cell tower A to cell tower B. Maybe during that switch, I get a new IP address. Maybe I'm on Wi-Fi, I'm just leaving my house, and I just, I cross the boundary where I switch off of Wi-Fi because my phone is connected to my house, and now it's connected to the satellite network, right? My IP address changes, my ISP changes, like everything about my internet connection just changed. But yet I don't have to log in again, right? So why is that? How does the website know that I'm the same person? It can't be based on IP address. You might think MAC address is another kind of unique address that computers and devices have, but MAC addresses can be spoofed. You can set it to anything you want. If you're interacting with me, I might know what your MAC address is, and then I could spoof you. Like, it would be very trivial to try and take over your identity if it was all based on Macs. So it has nothing to do with that. So why is it that a website knows that I'm the same person that's coming back? So think about it for a second. Okay, so the answer to this is going to be cookies. So what is a cookie? So first and foremost, what it is at a data level is it's basically just a number, or it's a piece of data, and usually there's a name for it as well. So a cookie will have a name, and then there'll be the value that it stores. Okay, so the name might be like a user identity or UID, and then the value for the UID would be set to whatever, probably hopefully a long, complicated looking string. And by number, I don't mean it has to be an integer. It's just data. So it could be a string. It could be an integer. For example, let's say you might have language would be the name of the cookie, and then English or French or something like that would be the value that's associated with it. Where does a cookie come from? How do you get one? So cookies are created by the website that you go and visit. So if you get a brand new computer, you turn it on, never been on the internet, you have no cookies. You have 0 cookies. And when you go to a website for the first time, what the website will do is you'll say, hi, I want index.html. And the website will say, okay, no problem. Here's index.html. But by the way, I'd like you to set... I saw when you asked for it that there weren't any cookies created yet. We'll get to that maybe in a second. But anyways, it will say, I want to set a bunch of cookies. And so it's an instruction to your browser. So that instruction comes into your browser. Your browser sees that this website wants to set a bunch of cookies. Assuming that your browser settings permit it to, then your browser will create those cookies. And and so they're marked in a set cookie header. And then what the browser will do is it's going to store that cookie value. And it's also going to remember the website that you were visiting when you got that cookie. Okay, and based on that information, it's going to do something with that in subsequently. And there's some rules and things like that, like little details that we have to go through. But in general, what it's going to try and do is every time you go back to the same website, it's going to send that cookie back. Okay, so future requests that you make to that same website, and we'll talk about what it means to be the same website in a lot of detail. The browser's going to, first it's going to check really quickly, like, do I have a cookie that's stored for that particular website? And then if it finds one, then it's going to put it into the header of the request itself. Okay, so every time you go to the website, you're sending the cookies back to the website. All right, so how does this solve the sort of Google Gmail kind of problem that we had? And so the answer is it solves it by when I log into Gmail, it sets a cookie, and then it will set a cookie that is kind of like a password. Like it will choose a long random number, and it will say, okay, this is your unique identifier. And in the back end, it's going to associate it with my particular account. And then when I come back, every time I come back, I'm going to send that same cookie value. And so it's going to keep seeing that same cookie value. And every time it sees that cookie value, it's going to know that I'm me. And then it doesn't have to ask me for my password anymore. Okay. Well, again, we'll talk about details here in a second. Okay. Now, how does the browser decide whether or not to include that cookie? That's what we need a policy for. So that's the whole purpose of this class is let's talk about what that policy is. Okay. So do I always send every cookie to every website? Do I try to only send it to the websites that set it? What does it mean exactly? Maybe they're related websites, but they're not exactly the same website. Like what exactly is the policy about when I send this cookie back? Okay, so this is just the same thing in sort of pictorial form. So here we have Alice, and say she asks Gmail for her inbox, and Gmail says, I don't know who you are, why don't you log in? So that's a request. So the give me the login page is a request, or give me my inbox as I'm logging in is a request. What the backend database has, we've seen this before. Well, we've seen the first two columns before. Is we have Alice and we have maybe a hash, maybe a salted hash of Alice's password. And then now what we're going to do is we're going to introduce a new value, which we're going to call as a user identity or session ID. So SID stands for session ID. And again, it's sort of a password-like kind of object. So it's just a sort of random string. And what the server will do is it will associate the cookies it's handed out, the session IDs that it's handed out with the particular users themselves. Session IDs should be unpredictable or random. If I can guess what your session ID is, then I can log in as you. Okay, so I'll go back to the website, but I'll use your session ID. And then because the website is just it's trying to figure out if I'm the same user coming back, yes or no. And it's based solely on this value. I'm not presenting my password. I'm not logging in again. So my ability to cough up this particular number governs whether I get into the website or not. Okay, so in other words, so it needs to be unpredictable and random. It also needs to be encrypted. So we don't want anyone that's in the middle to be able to read it. Okay, so even though it's in the header, it's still under HTTPS. Okay, so HTTPS will encrypt headers as well as the body for any information that's going back and forth. Header, it's a little bit of a confusing discussion because the SSL packets or TLS packets themselves have headers. So the header of a TLS packet is not encrypted. But this goes to networking. You don't really have to know these details at all, but just for your interests, networking kind of works like a stack. So you sort of have packets that are inside of packets that are inside of packets. And so all this cookie stuff is happening sort of at the HTTP level. HTTP as opposed to, I don't know, I'm sort of not explaining it well, but anyway, so it happens in terms of like exchanging HTML information. You have the body of the HTTP, you have the headers themselves. All of that gets put into what's called a TLS record. And the TLS record will include everything, but then the TLS record itself will have a header, and that header would not be encrypted. That header would include things like the IP address. So we noted that before, if you go to a website and you're going over HTTPS, someone in the middle, if they look at the packet, they know who you are as the sending IP, and they know the domain name that you're visiting because they know the IP address of where it's going. And they can turn that into a domain name by doing a reverse DNS lookup. So anyways, long story short, with or without the networking details, OSI model stack stuff, the cookie is part of the encrypted payload of it. So you don't have to worry about cookies being on the outside of the TLS envelope. They're going to be on the inside of the TLS envelope. Now, if you're accessing a website, okay, and the website is not going over TLS, okay, then you could pull that cookie value out if you were in the middle. And if you pull that cookie value out, then what you can do is you can create a connection to that website, use the value that you pulled out, and you now are that person as far as the website is concerned. It's more or less as good as having someone's password. Okay, so if you're able to lift someone's session ID, put it in your own packet, then when you visit the website, you're just automatically logged in as that person itself. So you've probably heard the term session hijacking. And so session hijacking is exactly this attack. It's getting someone's session ID, lifting it out of their packet, putting it in your own packet, and now when you visit the website, it's as if you are that user and you're already logged in. So session hijacking is it's more or less as powerful as stealing someone's password. Sometimes, and you'll notice for websites, what they'll do is if there's some like deep administrative settings, like say you want to actually change your password or you want to delete the account or things like that, what the website will do, even though you're logged in, is they'll make you log in a second time. They'll say, okay, you know, in order to do that, you need to supply your username and password. And so the reason they're doing that is because they recognize that it's easier to steal someone's session than it is to steal their password. And so what that does is it prevents, if you get session hijacked, then the attacker, you know, they can do a lot of damage, I'm sure, but they can't do complete damage. There are a few administrative things that they will not be able to do without supplying a website. So again, that's up to the website themselves. They decide how that looks. That's a policy, you know, for the website themselves in terms of which are the administrative functions we're going to put behind requiring a second authentication or a password itself. But anyways, if you ever, you know, go to change your password and ask you to log in again, that type of thing, then you'll know that that's the reason why. The other thing I wanted to do is tell you a quick story. So this is about something called Firesheep. Firesheep this is an old story. I apologize, a lot of my stories are old. This goes back to 2010. But what happened is that back in 2010, lots and lots of websites did not run over HTTPS. The way they worked is you would go to the website, they would ask you to log in. They knew that, passwords were sensitive. You don't want passwords in clear text going across the network. And so what they would do is they would throw you onto an HTTPS connection. They would take your password from you. And then once you've logged in, they would set a session ID and have the session ID, stored. And then they would throw you back onto HTTP. And the rationale there was that HTTPS is expensive because you're encrypting a lot of data. And so if, maybe it's like a website like Facebook is a classic example from that era. So Facebook, there's a lot of images and things like that. And so they don't want their servers to have to encrypt every image every time it sends it to a user. And so the thinking was that HTTPS was prohibitively expensive, so let's use it just to get the sensitive information, which is the password, and then get off of it as quickly as possible. Now today, encryption is built into the hardware level, like the chip level of most web servers and things like that, and so the cost of doing HTTPS is negligible over doing HTTP. So there's no performance difference at all. But anyways, that's sort of beside the point. Now people also understood that in theory, if there was a man in the middle, you could pull the session ID out after you've switched back to HTTP. And with that session ID, you could log in as the user that you stole their session from. So in other words, people understood that session hijacking was possible. In fact, it was easy, but the hard part was getting in the middle, right? So it's very, very difficult to get into the middle normally of most connections. So it was sort of marked up as a hypothetical attack, but one that no websites were really protecting themselves against. Then what happened is someone said, let's take this attack and make it super easy as possible. So what they did is they developed an extension that you could install in your browser. So you didn't even have to install any new software. You just got an extension for your browser. It worked in Firefox, and it was called Firesheep. And what it would do is if you were on a Wi-Fi network and it was public and it had to be configured in a certain way, but in a very common configuration, what it would do is it would kind of poison the routing tables in the Wi-Fi network, and it would get it so that everybody on the Wi-Fi network that was connected alongside of you, all their traffic was going through you. So you were the man in the middle for that particular Wi-Fi router. And normally, if HTTPS is enabled everywhere, it's not a great thing that someone can connect to your Wi-Fi and become a man in the middle for your Wi-Fi network. But at the same time, it shouldn't really matter that much if we're using HTTPS. But back in this world, we weren't using HTTPS. So you couldn't steal people's passwords, but what you could do is you could steal their cookies. Now, a second sort of challenge is, okay, you see some network packets go by. Do you know how to reach in, figure out which cookies are which? And then, you're going to reconnect to the same website. And when you connect to the same website, you're going to send that hijacked cookie. There's a technical sort of hurdle or challenge there. And so what Firesheep did is it also completely automated that process as well. So the user experience of using Firesheep was you go to, say, Starbucks or somewhere that has a public, say, a library, Concordia Library. You log on the Wi-Fi. You open Firesheep. It just opens a separate window. And what happens is that people's social media profiles, it supported Facebook, Twitter, and other ones that were popular again in 2010, they would just show up in this side window, with their username and their picture. And then if you want to be them, you just double click. And then boom, now you're looking at this person's Facebook account, or you're looking at this person's Twitter account. So it really, really, it took an attack that was sort of difficult to do and made it so slick and easy for users to do that, it just became this sensation in terms of the media, and everyone was freaking out about it. And, people were doing this. And so then what happened is that all the social media sites, they switched. So here you can see, this is for Facebook. You can see what it looks like. So you have this extension. You can see there's a bunch of accounts, Google, Flickr, Twitter, Facebook. And I just like double click on it, and then boom, I'm into that person's account. So anyways, sometimes, there's a few events that like really caused the world to change in terms of security, and Firesheep was one of those events. So it was one of those events that made lots of people turn HTTPS on, not just for collecting passwords, but like the entire duration of when you're logged into a website, you're using HTTPS for the entire duration itself. Okay. So let's go back to our picture here. So what Alice did is she sent a request. What the mail server did is it sent back, it said, okay, I want you to set this cookie. This is the value of the cookie. And although I said that this is Alice, that's for your information, but the web server here doesn't know that it's Alice. All it knows is that some user came and they asked, to log in or see their email or whatever. At this point, we're going to assume they haven't put their password in. And so what it does is it will create a sort of entry, and it will say, okay, I have a user. I don't know who it is. So I don't know their password because I don't know who the user is, but I'm assigning them this session ID. And then if that user ever comes back, the idea is that I'll know that they're the same user. I won't know who they are, but I'll know that at least they're the same user that's coming back to the website. Okay, and so when they send this set cookie to Alice, what Alice's browser does is it says, okay, this is a message to me. And so the browser has a file called the cookie jar, and the cookie jar has all of the cookies that it's set for every website itself. So what it will do is it will put this new cookie into the cookie jar. So the value of the cookie is this. The name of the cookie is this. Both of these things are decided by the website. So the website mail server, in this case, it can decide, it can name it whatever it wants, and it can put whatever value it wants in it. And then what Alice's browser will remember is when I got this cookie, the website I was browsing was mail.google.com. Okay, so that was the website that I was browsing at the time that I got this particular cookie. Now, there's a little bit more inside of the cookie, and we're going to get there in a few slides. There's a bit more information, but anyways, just for now, this is a simple view of it. Then what Alice will do is, let's say she's going back to mail.google.com, like now she's ready to say log in and send her username and password. She creates her request, but the browser will intercept it. It will say, okay, I see you're about to send a request to mail.google.com. Let me quickly go over to my cookie jar and just see whether or not I have any cookies that belong to mail.google.com. It sees that, oh yeah, I do have this cookie. And so what it does is it puts it at the start of the request. Okay, so now the cookie goes back to mail.google.com. Now, you might think, oh, mail.google.com would be like, okay, that makes sense because I just sent Alice this message and now I'm getting a response back. But remember, Google has 1 million people that are connected at the same time. People, they change their IP address, their devices change it and things like that. And so Google has no idea, like it looks on this slide like it knows when the second request comes back, it knows that it was the person that it just responded to. But the truth is Google doesn't know that at all. Okay, it doesn't want to try and keep track of that information. Okay, so the reason that it knows that this is the same person that it sent the response back to is because of this cookie value, because of this session ID. That's the only way that it knows that it's the same person. Okay, so it receives this request. It's almost like I got this request from someone, I have no idea who it is. Let me go check real quick. So it will go back to its table and it will say, oh yeah, okay, I see this cookie before it's in my table. I recognize it. I don't know who it belongs to. Okay. Now this table, I should mention a few things about it. This is up to Google themselves. So the way they implement the table is how they want to implement the table. There's nothing about the browser or Alice. Alice has no say. No one can see what this table looks like for any web server itself. Maybe a cookie value gets sent and it's not in the table, right? then it's up. What happens? The mail server, how it handles it is up to the mail server. So the mail server can decide whatever it wants. First off, it would know that it has never seen this user before. It might create a new entry using that cookie, or it might say, I don't know who you are, and it might try to set a new cookie that it chose. Notice that Alice could send any cookie here she wanted to. So, or she could change it. Her cookie jar is located on her computer. She could go in and change the value of this cookie if she wanted to. And again, that's how you do session hijacking. If I have your cookie value, I go into my cookie jar, I change my value to your value, and then I send it. But I could also just make up random values and things like that. So the mail server, we can't say how they're going to handle, cookies that don't match and things like that. Okay, then later, let's say that Alice is going to log in. So she's going to send her username and her password. Again, because she's going to mail.google.com, her cookie is going to go along for the ride. So it's always going to go to every request to this website. Now what the mail server will do is it will say, okay, looking at the cookie value, I see the cookie value. It's in my database, and assuming that the username and password is correct, then now I know this is Alice. Okay, before I didn't know who it was. Now I know it's Alice. It's the same person here, and the same person might have multiple session IDs. Usually, again, this is a good point to emphasize again. The cookie jar is maintained by your browser. What does that mean? That means if I have a computer and I have 3 browsers on it, if I have Safari, Chrome, and Firefox, the cookies that get set when I'm using Safari are not transferred over when I use Firefox, or not transferred to Chrome. Okay? And if I have multiple devices, the same probably is true. It's the same in the sense that, if I'm using Safari on my computer, I'm using Safari on my phone, those are different browsers. They're different software implementations of the same software. And so the cookie that gets set on one won't get set on the other. Now, there's a big exception to this. The exception is that if you're using a browser that's provided by a company, say it's Firefox, say it's Google, say it's Safari, Apple, and they know for usability reasons that if you set a cookie on one instance of a browser, say I'm logged into Apple and I set it on my computer, Apple may take the prerogative to synchronize those cookies to my iPhone, because my iPhone's also logged into my same Apple user account, and I'm also using Safari on my iPhone. So in that case, it will pass the information back and forth. Okay, so generally, cookies are scoped to a particular browser. So if you have multiple browsers, it's just for one browser. And if you have multiple devices with or without the same browser, it's also going to be scoped to that. But companies will try to synchronize your cookies just so that you don't have to always be logging in on every single device itself. Okay, so back to this. So once it recognizes that Alice is there, it doesn't really matter that she has more than one session ID. That's normal. Lots of people have different browsers or different computers and different devices and things like that. And so it's not going to freak out about that. It will just have 2 entries for her. And if Alice ever comes back with either of the 2 session IDs, then it will associate this as being Alice who's visiting the website. Again, another thing to say maybe here is because the cookie's associated with the browser, it's sort of obvious, but it's not associated with you as a person, right? It's not Alice herself. So if you share your browser with someone else, then if you log into one website and you don't explicitly log out, then what will happen is the next person will sit down at the computer and you'll still be logged in, right? That browser is still logged in. It doesn't have a notion of who the person is, okay? So sometimes you'll go to websites usually like government websites or things like that, and they might have an extra box when you're logging in that says, I'm using this from a public computer or something along those lines. And then what it's going to do is it's going to be a little more stricter about not honoring someone that comes back with the same cookie, particularly if the browser window closed, or maybe it will have an aggressive timeout. Like if there's inactivity for as little as 2 minutes or something like that, then it might stop dishonoring on the cookie itself. Okay. Now, I can't remember if I have slides about this, but since I'm on to this topic, I'm going to explain it now, and then we'll just go through it a little faster later. Let's think about two different settings that you might see on a website when you visit it that have to do with cookies, whether you realize it or not. And then I also want to talk a little bit explicitly about like what does it mean to log out and that kind of thing when it concerns cookies itself. Okay, so the first thing that you might notice when you log into websites, there'll be a box that says keep me logged in. So keep me logged in means basically that the cookie is going to persist. Now, let's say you don't check that box. So I go to Gmail, it says, do you want to me to keep you logged in? I say, no, I don't. It's still not going to be the experience where I type in my password to get my inbox. I have to type my password in to get message 1. I have to type in my password to send a response to message 1. Like I have to type my password in for every action. Okay. So what it's doing is it's still setting a cookie. It's still recognizing me based on the cookie itself. The big difference is that when I close the browser, it's going to stop keeping me logged in. So something's going to happen to that cookie, and the event that triggers it is a browser close, and then I won't be logged in anymore. Okay. Now I want to be. I'm wording this very carefully because we have to think about what that event is. Okay. The other setting is some websites have a logout button, right? You press the logout button. And then when you log out, presumably the next time you go back to it, you have to put your username password in. So your session isn't working anymore. Okay. So what's happening when you log out or when you close your browser window without having made this setting? So what's happening there's two places this could happen. It could be that your cookie jar is actually deleting that cookie. Okay. If the cookie gets deleted from your cookie jar, then it will never get sent again. And then that's fine. You can see why that would log you out. The other thing it could do is it could be some setting that's happening at the server side. So maybe the server's deleting the cookie, or it could be more simply like just marking you as logged out. Like, oh, this is the cookie, but now that should be considered a logged out cookie itself. Okay, so when you set a cookie, the website could choose to have it delete itself when the browser window closes. So that's one possibility. So if you're relying on the browser window closing to delete a cookie, then that is a setting that the web server could use when they ask to set a cookie. They could give it an expiration that will close when the browser closes. Okay, but if you go to a website and you click the log out button. Okay, it's like the cookie was already set. It was set when you logged in, right? So now maybe the website will try to like reset that cookie or change the settings of the cookie. But generally what happens is when you log out is the cookie doesn't disappear. Okay, so the cookie is still there. You keep sending it to the website. The website still knows it's you, but what the website will do is they'll just mark it as being logged out. Okay, so the website will just say this cookie, the user requested that they be logged out. So I'm no longer going to just, if I see this cookie come back, I know it's Alice that's coming back, but at the same time, I'm going to ask for her username and password. Okay, so again, it's a website policy that's being set. It's not something usually implicit with the cookies themselves. It's usually nothing that's getting changed on the user side. Okay, so the user is still sending the cookie. So again, with another example would be, I'm doing my Gmail on a computer that I share with other people. Say I click the sign out button. Someone else sits down at my computer. They type in Gmail, right? What will happen is my cookie will still be there and it will still get sent along. What changed when I click the logout button is that Google's saying, okay, I'm no longer honoring this cookie. Okay, I still have it. I still know who it was that was logged in the last time. But because they asked to be logged out, I'm going to make them submit a username, password, and then who knows, maybe it will be a different person that submits it the next time. Okay. So anyway, so that's just some details on how you kind of get rid of cookies. Another thing is a user can delete a cookie at any time. So anytime you want, you can go into the cookie jar, you can clear it out, you can delete it. Another option that you have is private browsing mode. So there's some confusion about like what is private browsing mode? What does it do? Is it like Tor? Does it hide your IP address? You know, like what exactly is different about? I know it doesn't keep a history, so that's like the sort of selling feature of private browsing mode. But aside from not keeping a history, what it does is it actually deletes your cookie jar for that session, for that private browser window, but it doesn't touch your cookie jar for your normal browser session. So sometimes if you're having trouble like logging into a website, or you're in some sort of loop where it tries to log you in and it's looping or something, or there's all sorts of weird like kind of technical things, a good debug thing to test is open up private browsing mode, go to the website in private browsing mode, and what it does is it basically, like, it's like you just bought a brand new computer and you never turned it on or you're turning it on for the first time, never been connected to the internet. It has no cookies, it hasn't picked up anything from any other website, and it's like a freshly installed browser when you go to it. Okay, but it's different than going and deleting your cookies, because once you delete your cookies, then like every website that you've logged into, you now have to log into again and things like that. Okay, so anyways, that's what private browsing mode does. Okay, users, you have your cookie jar is your own. Okay, so you can do different things to control what cookies get set. You might configure it so that you never accept any cookies. You can just turn cookies off. If you do that, you'll struggle being able to access almost any website that requires some sort of login or something like that. You can disable third-party cookies. So these are cookies from third parties. We'll kind of go through what that means in a couple slides. And you can clear your cookies at any time, and then the browser will empty your cookie jar. You can also set your browser so that every time you close the browser window, it clears the cookie jar. So that's another setting that you could use. Or you can manually go in at any time and clear out your cookies. And then private browsing mode is kind of like a temporary clear. So it clears it for, as long as you're in the private browsing mode window, you get a fresh cookie jar with no cookies in it. Now, as you use private browsing mode, like say I open private browsing mode, the first thing I do is I go to Google. When I first go to Google, that first request has no cookies because I have nothing in my cookie jar. But then Google right away is going to want to set cookies, and private browsing mode will accept them. So it will accept cookies. It's not like a mode where cookies are disabled. It's just a mode where you start with no cookies. So you start from scratch. You start with a fresh cookie jar. And then as you use private browsing mode, it will pick up cookies. And then when you close private browsing mode, because it's not your real browser, it's this temporary browser, then it will clear the cookie jar again. And then next time you open private browsing mode, you'll again have a clear cookie jar. Cookies will eventually expire. The server has control over that. If they want to make your cookies expire in 40 years, they can do that. So you can't really rely from a user trying to control their cookies. You can't really rely on expirations to do anything meaningful. And then for assignment 2 in this course, you did a usability study where you looked at some extensions that would help you manage cookies and see cookies, and maybe do like a site-by-site sort of thing, like I'll accept cookies from this site but not from this other site. Or in terms of the cookies themselves, I'll accept any, if Google wants to set a cookie on a website that's not Google, that's fine, but I don't want Facebook to do the same thing, or whatever the example is. And then the server, as I said, it controls its cookies. And so whether it clears your cookies or not, like say you tell it to log out, you have no control. You can't see what it's doing on the server side. So you have no ability to know what the server's doing. Okay, and then the two examples being the keep me logged in and the logging out, explicitly logging out. Okay, what do cookies look like? So let's say we go to a website. This is an example of TSN. We can actually do this. Okay, I don't know why that took so long to load. But anyways, here I am. I'm on TSN. We'll use our friend that we've seen from previous lectures, Inspect Element. So this shows me lots of different information about the website itself. I have everything that was loaded on the website. We'll be looking at some of these other tabs next class. And then if I go into, let me see if I can find it. Storage. So if I go to the storage tab, this is basically everything that this website wanted to store on my computer. And so cookies is one of the categories. Okay, so you can see I have a bunch of things that want to set cookies. You can see for tsn.ca, there are a bunch of cookies that are set. I'm just noting that I'm not signed in, so I hopefully won't get session hijacked by putting this video on YouTube. Yeah, you can see that there were a bunch of websites that wanted to set cookies. That's why they're in this list. But for whatever reason, my computer didn't accept it. Okay, so it didn't accept to store these cookies. And the main difference, what's the difference between TSN and these other things is, well, I'm on the website TSN, up here, sorry. I'm on the website TSN, and the cookies are being set by TSN. There's a match there. But that's not true of any of these other things. Okay, so these are what we call third-party cookies, which I noted before. Now, what's happening here is my browser is when you get a browser for the first time. Now it was different 10 years ago or 20 years ago, but now when you get a browser, it's going to have some settings that make it harder for you to be tracked by cookies. Okay. So what I can do is I can go in here, for example, I can unclick prevent cross-site tracking. Now when I load the website, it's going to be a little bit different. So you can see some of these third-party websites were able to set cookies. And you might also notice that a lot more, it's sort of like when the website woke up and realized that, oh, I'm not blocking third-party tracking, then there was a whole bunch of extra third-party tracking cookies that were added. Okay, so let me first re-enable that setting, and then we'll go back to the slides. It sort of shows the same example. Okay, so we have a bunch of cookies for tsn.ca, and then we have a bunch of domains that when I load TSN, these are domains that are also getting loaded at the same time. And the name of the cookie is being chosen by tsn.ca. So if they call it permutive ID, that's the name that they chose. That's fine. They also choose the value to put into it. Sometimes the value just looks like a random string of numbers. So for things like user IDs and things like that, that's what you might see. Sometimes they're numbers, so you can see this is a number 1. There's 1.1. It kind of looks like some sort of addressing system. Sometimes it's more like code, so you can see here there's this success true, so this is like a JSON string. This says the word true, so like a human can look at that and read it. This is kind of like URL parameters that are being set. So what the value is, it may be some machine readable thing, it might be a human readable thing. It really depends on who's programming and what the purpose of it is. Another thing you might notice that there's tons of cookies. So I sort of gave the impression that you go to a website, it sets a session ID, and then that's sort of it. But in reality, websites set all sorts of cookies for all sorts of things. Cookies don't just govern logins. So logins are one component, but everything about the website gets governed. Like, for example, if you choose to go to a website, it displays it in French because we're in Quebec by default, but you're able to trigger it to display in English. The website may be programmed to set a cookie to remember that you switched to English. Then if you close your browser, you come back tomorrow and you go to the same website, it will show you the English version now because it remembered that you want to have access to the English version. Okay, you might zoom in, you might zoom out, you might put on like dark mode or night mode for the website. lots of different things that you might do with the website itself. All these things can be stored in cookies, and then when you go back to the website, you get the same sort of experience as when you left the website for the last time. Okay. The next field, so you have the name field, which is set by the server. You have the actual value, which is set by the server. So we're sort of moving through this diagram from left to right. The next thing is the domain. What this says is when the cookie should be sent back. And what your browser is going to do is it's going to remember that this cookie was set when you went to tsn.ca. And so it's going to do a comparison between these two. And it's going to decide whether it can return the cookie to you. And we're going to have some slides that show like what's the .tsn.ca mean as opposed to, say, just tsn.ca and things like that. Actually, okay, maybe it's here. But so tsn.ca, what that means is it will send it to either an exact match. So if you are exactly visiting the domain tsn.ca/whatever, then it will send it. But if you're visiting, say, a subdomain like images.tsn.ca, then it will also send it as well. So you can think of the dot here as an asterisk or a wildcard. So it basically is like either the exact domain or any kind of like subdomain of it. Okay. This doesn't have a dot, so it says www.tsn.ca. So it will only go to www.tsn.ca. It won't go to any subdomain of that, not that there would be one. And it won't go to any superdomain either. So if it was images.tsn.ca, it wouldn't go to that. If I wanted to share the cookie between www.tsn.ca and between images.tsn.ca, then this is how I would denote it. Okay. And you can't like limit it. You can't say, okay, here's 3 subdomains and I want to share it with those, but not with any of the others. It's sort of all or nothing. You sort of take it. Okay. The next thing is this is probably a mistake. Okay. So what this says is it will match either exactly to www.tsn.ca or it will match to the subdomain of www, but you generally don't have subdomains of www. So that looks like a mistake, but that's what it means. It means it would match to exactly this or any subdomain of this particular string. Okay, the next thing is a path restriction. So you can also say only send it back if it's tsn.ca/images/whatever. Basically, nobody ever uses this, so you as far as this course is concerned, you can more or less ignore it. But it is there. You could restrict a cookie to not just a particular domain, but a particular path as well. Then you have your expiration. So how long is this cookie going to be kept around for? The expiration is either a date, usually with the time. It wasn't I didn't pull it open far enough for you to see it. And then you also have the word session. What that means is until the browser window closes. So once the browser window closes, then it will get sent. Okay. Next thing is the size of the cookie. The size is basically just a function of how much data you're putting into value here and how long the name is. Okay. Everything else is constant size. So, for example, here you can see _GAT, so that's only 4 characters. The value that's being stored is only the number 1. Okay, so that's a really small cookie, and you can see, yeah, it's only 5 bytes long. And then some of the other ones, this one I was looking at, it looks short, but actually the name is really long, and it's the value that's short. And so that one ends up being 42 bytes. This one has a really long name, it has really long data, it has 290 bytes. So anyways, the function of how big it is basically just what you're seeing on the screen. Okay, then you have some security flags. So the security flags are secure and HTTP only. We'll talk about those. I think there's a slide. Actually, okay, we'll talk about them now. Okay, what does secure mean? So what secure means is I'm going to set a cookie, and presumably when I set the cookie, you're visiting my website over HTTPS. If you ever come back to my website, I only want you to send this if it's over an HTTPS connection. Okay, so if you're going to tsn.ca and it's over HTTP as opposed to HTTPS, your browser will still send all the cookies where this check isn't marked. Okay, so all those cookies will still get sent, but the ones that are marked, it will not send. Okay, it will say it just won't send them. That's it. No error message, nothing like that. It just won't send them along. Okay, so if, for example, you have a session ID, so a cookie, and the value of the cookie is basically like a login credential for this website for a user, then what you want to do is you want to make sure that that's marked secure. Some websites they mark everything secure because the whole website is always served over HTTPS. So that's kind of like the best thing that you would want to see. And then for websites like this, there's still a mix of secure and unsecure cookies. Okay, the next thing is HTTP only. Now, if you look at that, it kind of looks at like HTTP as opposed to HTTPS. So you might think it's kind of the opposite of this cookie or something like that. But it actually has nothing to do with the distinction between HTTP and HTTPS. The distinction here is there's basically two main ways that a user would go to a website and submit a request. Basically, go to a website and say, give me, like, say, the HTML file that's here, or give me this image, or give me this JavaScript. Okay? The first reason is that the user somehow navigated to a website. Maybe they typed in www.google.com, they clicked on it, they opened a bookmark, something like that. But basically, the user browser initiated this request. The second way is they downloaded some JavaScript, and the JavaScript started running. And when the JavaScript started running, it decided that it wants to go visit this website or pull this data or fetch this image or whatever it is. Okay. Now, when JavaScript initiates a request for information, it uses this protocol called XML HTTP request. Okay. It looks different. So your browser, when it sees, like, you go to a website and all of a sudden you have to load 10 different images or 100 different images from all sorts of different servers. When your browser has that sort of bird-eye picture, it knows which of those were created by, like, the HTML of the website itself and which of those are being requested because some JavaScript is running. Okay, and it can distinguish between the two of them. Now, because JavaScript can just load any resource that it wants to, sometimes people worry about what happens if you get bad JavaScript running. Next class, we'll talk about cross-site scripting, which is essentially that attack. And so as far as cookies are concerned, what you could do is you could set your cookie so that if JavaScript ever comes back to TSN, you don't send those cookies along. So those cookies don't go along. Now, I will note here, you might be concerned, well, like, does the JavaScript see it? Like, somehow I get JavaScript running on your website and I as the JavaScript go and ask for google.com and a bunch of cookies associated with Google get thrown into that request. Does the JavaScript see those cookies? And the answer is no. Okay, so all it does is it creates a request, but what happens is that those cookies will go along for the ride. We're going to see why that's a problem in a little later in the lecture with something called cross-site request forgeries. But anyways, for now, HTTP only is another flag that you could set so that any requests originating from JavaScript wouldn't be run. Okay, then I showed you this already, but your browser will probably have some settings to try and limit cookies. And so if you unclick that, and you reload the website, you'll see that all of these cross-site URLs are also being able to set cookies, and you might also see that there's more, sort of resources that get loaded here that want to set cookies as well. Okay, now I want to go back to all the way back to here. So we talked about what does it mean to match. Like, does this match TSN and things like that? So I want to revisit that with a little bit more detail and give you a concrete example of what matching means. Okay, so let's say that I'm going to a website. The website is encs.concordia.ca. Okay, and encs.concordia.ca is setting the cookie. Okay. And when they set the cookie, they're able to decide what domain what domain should match this website when someone comes back to this website, should the cookie be sent, yes or no? Okay. And so there's going to be some rules. This is where the policy itself actually kicks in. It also has to do with something called origins, and origins are important for this lecture and also for next lecture. So the origin for the cookie itself, the website that set the cookie, is encs.concordia.ca. It's putting a rule in for, if I go to other kinds of domains, should the cookie be sent or not? And essentially what the policy would be is, if the origin is the same, then send the cookie. And if the origin is different, don't send the cookie. Okay? So this is sometimes called same origin. And it's sort of the same rule that's in the same origin policy that we'll talk about next class. Okay? Same idea. The same origin policy it is about JavaScript, not cookies, but it was created looking at the cookie policy and trying to match the cookie policy itself. Okay, so if encs.concordia.ca sets a cookie and they say, I only want it to be sent back if the user is visiting exactly the same domain that I am, then that's fine. The browser's like, that's great. That's the normal scenario that we're expecting. Okay, it's an exact match. Okay. So sorry. There's actually kind of like three things here. I should maybe have a diagram on the side that shows this a little better. So there's three like kind of origins that are being compared. So there's the website that you were visiting when the cookie was set. So that was, say, encs.concordia.ca. There's what's in the cookie itself. So what's in the cookie itself is, say, encs.concordia.ca. And then there's, what website am I visiting the second time? So the first time I was on this website, it set a cookie, and this was the domain that's in the cookie. Now I'm going back to this domain. Is this cookie being sent? Yes or no? And so the answer is yes, it is being sent, because all three of them agree with each other. Okay. Let's say I go to images.concordia.ca, or say canada.ca. In all three of those cases, this cookie is not going to get sent because none of these domains match the domain that was set. Okay, so I set exactly encs.concordia.ca. These are not exactly that. And so this cookie does not get sent by my browser when I visit any of these three domains. Now, what I can do instead is, am I allowed to ask for it to set encs.concordia.ca plus any subdomain of it? And the answer is yes. The browser says that's fine. If you're encs.concordia.ca, you're setting a cookie, you are allowed to set yourself, not just that it gets returned for your exact domain, but any subdomain as well. So in this case, if a user is going to exactly encs.concordia.ca, it will get sent. If they're going to say images.encs.concordia.ca, it will get sent. If they're going to just concordia.ca, it will not get sent, okay? Because it doesn't match this pattern. Okay, this pattern says encs.concordia.ca or any subdomain of it. Concordia.ca is a super domain of it, okay? It does not match images.concordia.ca. Okay, it has to start with encs.concordia.ca. Then there can be anything in front of it. So it could be nothing in front of it, or it could be images.encs, but it can't be a sibling domain. Okay, and if it's a completely different domain, it's not going to match either. Now, maybe I want to set those kinds of things. Okay, so maybe I do want my cookie that I'm setting here to be shared with concordia.ca and images.concordia.ca. That's a very natural thing. So what do? So the answer is, well, I can set it to be a super domain of myself. So encs.concordia.ca can set its cookies so they don't just get responded to itself or sort of subdomains, but it can go up a domain as well. So I can say, I want my cookie to be sent back to anything.concordia.ca or concordia.ca itself, okay? And the browser will accept that. So the browser says that's a valid thing that you're allowed to do, okay? So in this case, encs.concordia.ca, images.concordia.ca, just concordia.ca, any superdomain, well, any subdomain of concordia.ca, superdomain of encs.concordia.ca, this cookie is going to get sent. The only kind of website it wouldn't get sent to would be like a completely different domain, like say canada.ca. Okay. Now, what if I wanted to share my cookies with canada.ca? Can I go up another level and just do, say, a .ca? And this is where the browser will say, no, that's too far. You can't go all the way up. If you go all the way up to .ca, then, or say it was .com, which is a much more popular domain, the cookie one website sends, it's going to get sent to like every other website, well, every other .com website on the internet, and it's just completely unscalable. Okay, so browsers will not let you set something at the top level domain. Okay, you're allowed to go up to a domain, but not all the way up to a top level domain. Now, what if you're concordia.ca and you want to set a cookie for canada.ca? Okay. This is what we call a third-party cookie. It's basically you're visiting one website and it's trying to set a cookie for a completely different website. By default, this is going to nowadays it's going to be disallowed, but there are ways that you can probably turn this off. And it used to be the case that you were allowed to do this. The reason it's not allowed is usually a privacy reason. So we're going to go through the privacy example in a bit, but it allows too much. It makes tracing people across websites too easy. Now, let's say that we set a domain, and I mentioned there's this path field. No one ever uses it, but it is there. So let's just consider one example. So what I could do is I could set the same domain and I could set the same path. Then what that means is, what that means is if I visit this website / this, it's fine. Any sub path along this is fine too. But if I go to a different website, for example, Manon's website, then it's not going to work. Okay, so this is hopefully a review, but I'll just keep going over it just to make sure that we're getting what happens. So normally when I go to a website, the website usually has a bunch of like ad libraries and a bunch of weird stuff like that. And so what it will do is it will say, I want you to go and request JavaScript or other like images and things like that, other resources from a bunch of other domains. So say from Google, Snapchat, DoubleClick, Twitter, that kind of thing. So what happens is I create all these outbound requests, what my browser does, okay? And the browser intercepts it, and it says, okay, I'm going to check all of these against my cookie jar, okay? Now, because this request is going to google.com, it doesn't matter that TSN is the website that's being visited, okay? What I'm looking for in my cookie jar is, are there any cookies that were set when I was visiting google.com previously? They're set up in such a way that google.com is a match for the website I'm now visiting, which is google.com. If that's the case, then I'm going to throw the cookie in. So if there's cookies for Google, it gets thrown into this request. Say I don't have cookies for these two websites, they don't get thrown in. There is a cookie for Twitter, so x.com now, I guess. So it gets thrown in as well. Okay, so what the browser is doing is they're checking where you're going. They're checking against the cookie and what's set in the cookie itself. And then they're doing some other checks like, is it expired? If it's expired, then it will delete it. And we mentioned those flags. So depending on whether this is over HTTPS or whether it's JavaScript that's initiating these requests, it may or may not send them as well. Okay, so your cookie policy is basically like going through this checklist of should I put the cookie in, yes or no, for all of them itself. Okay. Now, notice that this request, because it's going to google.com, even though TSN told me to load this resource from google.com, I am requesting the resource from google.com. So the cookie that's getting sent is google.com's cookie. TSN does not see this. TSN is not on the wire. So TSN it made me request something from google.com. My browser said, wait a minute, you're about to go to google.com. I'm throwing Google's cookie in with it. But the only person that sees that cookie is Google. Okay, so it's not seen by any other kind of cookie itself. Okay, so this is what we call a cross-site cookie. Okay, because the site that you're loading is making you create a request to another site, and your browser's throwing the cookie into this other site. So by going to tsn.ca, my Google cookie is being sent to google.com. That's a cross-site issue. Not an issue, but like a feature. Okay, that's to distinguish it from, say, a third-party cookie. So a third-party cookie is TSN trying to choose the cookie that gets sent to google.com. The cookie here that's being sent to google.com is a cookie that I happen to have on my computer because I've previously gone to google.com. It's not a cookie that TSN set. So TSN is making me send that cookie to google.com, but it didn't control setting that cookie. Okay, it kind of forces me to send that cookie, but it didn't force me to create that cookie or choose what the value is in that cookie or anything like that. Okay, so cross-site cookies and third-party cookies are different. They both involve, two different, like, cookies spanning two different domains, but they're different in terms of who set the cookie essentially. Okay, there's this little video. Because I'm recording this lecture, the sound's not going to go through. It's not going to play right. So what I'm going to do instead is you're watching this on a playlist on YouTube anyway, so I'll just throw this video into the playlist. If you want to watch it, you can. It's basically just a fun video that tries to explain cookies. It's only 2 minutes long. It's animated and things like that. But technically speaking, we've seen everything that's in the video itself. Okay, now that we've seen sort of the mechanics of cookies, and hopefully we're pretty comfortable with how cookies work, let's think about some of the ways that cookies go wrong. So what are some of the issues that we have with cookies? So the first thing we'll consider is third-party tracking. So let's just do this as an example. Let's say that I go to a website like Lululemon, and so I send a request for it. It sends it back the index. And let's say I'm looking at a particular shirt. So this is the shirt I'm looking at. I'm thinking of buying it. What will happen, what's possible that might happen, is that Lululemon, they want to advertise their products to me. Okay? So what they might do is they might subscribe to a third-party ad agency. And what the ad agency is going to do is it's going to sort of track all the people that visit the website and the things that they look at, and it's going to try and help the website in some sense in order to market to the people themselves. Okay, so this is what it may or may not look like. There may be an ad agency, let's call it Agile One. It's here, and what will happen is that the user will send a request because I downloaded index.html. Inside of it, it will make me load a request to agile.com. And what Lululemon will do is, because they're working with the third-party ad agency, is they'll also send along the item that I'm looking at. So say every item has a unique identifier. I'm looking at 9483. So that's the number that I'm looking at. Okay. So now Agile One knows that it doesn't know who I am. Say I'm not logged in or anything like that. But what it does know is that some user was coming here and that user was looking at this particular item. Now, if Agile One wants to track me, what they can do is they can give me a unique identifier. Okay, so they'll set a cookie. It will have a unique identifier. Usually the reason I'm requesting something from them is, I'm maybe downloading some JavaScript or something like that, maybe an image, I don't know. But this could just be a trivial thing where it doesn't actually need to send anything back other than the set cookie request. But anyways, it's going to set a cookie 55, and it's going to have a backend database, and it's going to say the user that has session ID 55, they're interested in this shirt 9483. Then later I'll go say to CBC. Okay, now CBC, they're kind of government funded, but they also need to have revenue, and one way that they make revenue is showing ads. And it may be the case that if, a user goes to CBC, they see an ad, they click on it, that somehow CBC they get more money than if they just showed the ad and the user didn't click on it. So it's sort of in their interest to try and show interesting ads to users and things that users might want to click on. Okay. So CBC may say, hey, we're going to work with ad agencies as well. So Agile One or whoever it is, we work with those people as well. So what will happen is I go to cbc.ca and CBC says, okay, go load an advertisement from Agile One. Okay, the same web server that was here. So what happens? Well, my browser sees I'm about to request something from Agile One. Do I have anything in my cookie jar that matches this? The answer is yes, I have this cookie that was set previously. It's in my cookie jar. Okay, so as I'm about to go to Agile One, it throws this cookie in and it sends this request. So from Agile One's perspective, it says, I just got a request for an ad. So I have to cough up some ad. I have lots of ads I can choose from. There's lots of companies that advertise with me. So I'm going to choose an ad that I want. But I'm noticing that I think I maybe have seen this user before because I've set a cookie for them. So they'll go in their backend database and they'll say, where have I seen user 55? And they'll be like, oh yeah, I remember. User 55 was interested in item 9483 from lululemon.com, right? So what advertisement are they going to show you? They're going to show you exactly, for example, an advertisement for the exact shirt that you were looking for. Okay, so you may have experienced this browsing the web where you're looking at some sort of product, maybe you're researching something, maybe you're looking at cars or something like that, and then you go to like news websites or third parties like that, and for some reason it's showing you like the exact same ads. It's showing you ads for the exact same things that you were looking at, right? And so this is what's happening behind the scenes. It's all enabled by cookies. It's also enabled, though, by having common parties that are sort of ad agencies that are behind all these websites, okay? So if CBC works with a different advertisement agency than Lululemon, then this cross-site tracking doesn't happen. Okay, you can't. And this is what it's called, by the way, cross-site tracking, because somehow what I was doing on Lululemon is somehow being tracked across when I go to cbc.ca. Okay. Now there are like ads, or there are companies that are on almost every website. So Google is on almost every website. Google doesn't necessarily use it for advertising. That's one of the features of it. Another feature is that it can cross over, it can try and figure out, the reason you would put it on your own personal website would be you want to get some insight into how people are finding your website. Like what website were they on right before they clicked on yours, right? And so if everybody enables Google, then Google can set a cookie and they can track users around, and then they can give you lots of information about who your users are and the other kinds of websites they visit and things like that. Okay, so as mentioned, we call this a cross-site request. So a cross-site request is when I go to one website and it makes me load a resource from a different website, and then my cookie goes along for the ride. Okay. Now, cross-site requests, you might, if you've heard of an attack called cross-site request forgery, which we'll talk about in the next slide, you might think this sounds bad. Cross-site request sounds like a bad thing. Okay. But cross-site requests are not bad in and of themselves. They're actually a good thing. Okay. What they do is they enable things like, for example, there's Facebook. I'm sure you're familiar with it, although it's not as popular today. It's a social media platform. They have the ability for you to share news articles that you've read and that you've liked. Okay? And the way you might do this is you might set the website. The experience that you might have is you go to CBC, you read the article, and it's not like you have to copy and paste the article because you liked it into Facebook. There's a button right on the CBC article itself. Okay, and it's like a thumbs up button, and if you click it, it will automatically like it on your Facebook account, and depending on how it's configured, it may do things like repost the article or create a post about the article itself. Okay. Another thing you may or may not see is when you're looking, even though you're on the CBC website, beside the like button, it might say 3 of your friends have liked this article. Now, sometimes websites do this for sketchy reasons, like it's just completely made up for engagement. But in this case, with Facebook, it's reputable. And like it's literally, it knows which friends of yours. It might even show you like the pictures, like the little icons for the exact friends that like this article as well. Okay. How does that all work? Is it that CBC is somehow asking Facebook, Facebook's telling CBC about your friends, and then CBC is displaying the information to you? If that's how it worked, that would be a violation of privacy, right? So the reason it works is because of cookies and cross-site requests. So what happens is CBC creates like a little box, like an empty box, call it an iframe, that's on the website, and it says Facebook's allowed to fill this box in any way they want. And so your user, your browser goes over to Facebook. It says, give me some JavaScript. CBC says the name of the JavaScript itself. Facebook says, okay, I see that you want me to give you the JavaScript for this like button, but I also see that you're logged into Facebook, okay? Or a cookie's coming along with you. Because this cookie's coming along, we're not allowing third-party cookies, right? So CBC didn't create this cookie. Because there's a cookie here on this request, the only possible way that this cookie could be there is because this user had gone to facebook.com with their browser sometime before this request is created, okay? So they already had a cookie in their cookie jar. Probably they have a cookie in their cookie jar because they're logged into the website. So let's assume that's the case. If they're not logged in, then Facebook will just show a generic like button. If you click it, it will say, okay, log in, that kind of thing. But assuming the user's already logged in, Facebook will recognize that they're logged in because they see the session ID, and they'll go look it up in their database, and they'll see, oh, I know this session ID, it's a valid one. I haven't canceled it or logged this user out yet, and I know exactly who the user is. I know it's Alice. So then what Facebook will do is they'll send back a like button, but it's customized with Alice's information. So they'll look up her profile and see that 3 of her friends have liked it, and they'll mix all of that stuff in, okay? Now, Alice's browser is weaving this content together. So it got some content from CBC, it got content from Facebook. So when the browser looks at when the user looks at the website, they see some stuff that came from Facebook, they see some stuff that came from CBC. From the user's perspective, looking at the website, they don't know what came from CBC and what came from Facebook. It all gets weaved together, or it gets mashed up, was the term that we used to use. Okay, so it's weaved together. So I don't know what came from where, but the browser knows. Okay, so the browser knows, and because it's all getting weaved together in the browser, CBC doesn't see anything about your Facebook, and Facebook doesn't see anything about CBC. So there's no information that's being shared between these two sites, unless if there's some attempt to try and either pass information back and forth. So we saw that actually in the previous example, where because Lululemon added this field to the link that went to Agile 1, Lululemon was sort of able to talk to Agile 1, so it was a way of passing information to it. So it could be that they are trying to pass information back and forth, or it could be an attack where like one of these two is an adversary. So maybe this is an adversary and they're trying to learn things about this website, or this website's an adversary trying to learn things about this. That we'll talk about next class. So those are variants of cross-site scripting that we'll look at. Okay, now another thing I want to talk about that doesn't have anything to do with cookies yet, but we'll need it later when we talk about an attack and how to fix the attack, is this is also something that has come up in previous lectures, but I'll spend a little more time on it. The way the internet works now is you go to URLs, they look like this. So take a second and look at this URL. So it's for google.com, search, so this is Google search. And you can see query equals soccer and page equals 10. What this URL represents is it represents the 10th page of results for the query soccer. Okay? If I click on this, I guess I can't click on it. But if I were to click on this link, say I copy and pasted this into an email, right? And you clicked on the link, you would go directly to the 10th page for the Query Soccer on Google itself. Okay, so this is a little different than maybe how you imagine a search engine to work. So you might imagine that when I go to Google, it says, what do you want to search for? I type in the word soccer, I press enter. It shows me the first page of results, okay? And then if I click, give me the second page, right? How does it know that I'm the same person that wants that second page of results, right? So we know that we have cookies now. So you might say, okay, the first time I go, I set a cookie, and then the website remembers, it writes down that the user with this cookie, they search the term soccer, and they're on the first page of results. So then when I click the next button, then they see my cookie come in, they go look up where I'm at, like what I was searching for, what page I'm at, and they know, okay, the next set of results would be page 2 of the search query soccer. Okay, so that is how the internet used to work. So it used to work that way. The problem with the internet that works that way is that Google is storing a lot of information. So every user, they have to remember what was the last thing they searched and what was the last page they were working on. It's a lot of what we call state. Okay, so they're storing a lot of state about the user. What they'll do instead is they'll write basically what the user's doing into the URL, and then they'll change every URL on the page. So for example, if there's a next button on the page, it will just have the URL google.com search query soccer page 11 instead of page 10, and that's hardwired into the page now. So when the user clicks page 11, the request that they get is right in the URL itself. So whoever clicked on this, they were searching soccer, and now they want page 11. And what this does is it frees up Google from having to remember anything. Okay, so they don't remember anything. All they do is they rewrite all the URLs so that the commands are in the URL themselves. Then they just they receive a URL, they do what the URL tells them to do, and that's it. Okay, so we call this whole architecture RESTful. So let's see how it might work in an attack. So now we're ready to talk about the cross-site request forgery attack. Okay, so this is an attack because forgery is a spoofing attack. You can put it under S in Stride. And this is how it works. So we have Alice, we have an adversary, and this attack only works if the adversary can lure you to their website. Okay, so they set up a bad website, and somehow you get lured into visiting the website. Otherwise, it's not going to work. Okay. Now, how do they get you on their website? It could be phishing. It could be, there's a million different ways to get a user to go to your website. And generally speaking, the web is set up, like the security of the web model should be that even if you end up on a bad website that's controlled by an adversary, they shouldn't be able to do anything seriously or substantial to you. Okay. Other than what maybe they display on the content of the website itself. But in terms of your security, it shouldn't be like you get a virus by just visiting a website, or you get your credentials stolen or things like that. Okay, so it should be like relatively safe to just visit a website. It's not something you necessarily want to do, but it the web is designed to secure you from this type of thing. Okay, so it's totally within the threat model that you might at some point end up on an adversary's website, and nothing bad should happen to you. Okay, but here's what happens is. So you download the HTML, and when you download the HTML can include links to anything. Okay, so any website anywhere that they want. Okay, so it could include a link to bank.com, and the link could have a bunch of parameters that look like this. Transfer 100 from Alice to Eve, and because the bank doesn't want to. They don't want to remember that a user logged in, they looked at their checking account, and then they clicked their checking account. Then they said, I want to create a transaction. And then they filled out the field, and then now they're about to send that transaction. The bank doesn't want to remember that full history of how the user got to where they are. So what the bank is doing, they're using this RESTful architecture. So they program URLs, and if they see a URL that says transfer 100 from Alice to Eve, then they're going to do what the URL tells them to do. Okay? So this is a problem because if the user has a cookie set, even though evil.com doesn't see the cookie, that cookie does get sent. Your browser says, oh, you're about to go over to bank.com. Let's look through your cookie jar. Oh, you have a session ID for bank.com, so I'm going to throw that in. And so this request that the bank sees, this first flow, it doesn't know that it was initiated by the adversary, as opposed to the user just using the bank app normally, because eventually they would get to the point where this is the kind of URL that would get created. Okay, so what the adversary can do is they can force the user to create this URL. The bank misinterprets it as something that the user was doing in the process of sending the transaction. Whatever the URL tells them to do, they'll do. So they might put this transfer through, send back a response confirming that the transfer went through. And now, just by visiting the adversary's website, Alice ended up transferring $100 from Alice to Eve. Okay, so this was a problem for the web that we kind of got rid of. I'm going to show you the trick for getting rid of it. But it was a problem, for a while. All right, so what's the trick for how do we prevent this, or how do we secure this from happening? Okay, so the trick is very, very simple, but it's a little hard to sort of understand. You have to kind of think about it for a while, I think, in order for it to sink in. Okay, what we're going to do is every time the bank doesn't want to go back to keeping state about everyone's, what buttons they were clicking on the website and how they got from website A to website B within the website itself. Okay, so they still want to use these RESTful architectures. And so what the bank's going to do is when they rewrite these URLs, they're going to throw in the user ID that's in the cookie itself. Okay, so the bank will say, every time you're actually doing something on the bank is creating URLs with instructions. It's almost like instructions for itself. If the user clicks this, do this action. If they click this, do this action. So they're putting all this stuff into the URL parameters. They always throw the cookie value of the user as well. Okay, and if they ever get a request that does not have the cookie value, then they ignore it. Okay, now they know the cookie value because they're the bank, so they can put this value here. And when they receive a request like this, the browser is putting the cookie here, right? And if the bank created this URL, the bank put the cookie at the end of the URL. Okay, because the two match each other, then we say it must have originated from the bank, right? The bank's the only one that could have put the value here. Okay, now in the cross-site request forgery case, could Eve put this cookie value here? She cannot. Why can't she put the cookie value here? Because she doesn't know it, right? She can force Alice to create a request that puts the cookie value in the request, but Alice's browser was the one that put the cookie here. Okay, Eve didn't see that. She doesn't see the cookie itself. Okay, so she can trigger Alice's browser into putting the cookie value into a request, but because the request is going to bank.com, that's the only criteria for the bank.com's cookie to be put here. By definition, Alice doesn't see it because it's going to bank.com instead. Okay, so she has no idea what the cookie is. And by the way, if she did know what the cookie was, she wouldn't have to do this attack in the first place. She could just session hijack Alice directly. Okay, so Alice can no longer forge this URL, even though this looks like a valid URL for bank.com, because it's missing this cookie element, which is the unforgeable bit. It's the bit that nobody knows except for the bank and Alice herself. It's a shared secret between the bank and Alice's browser. Those are the only two parties that know it, so no one can forge a URL for a website that they don't know. Okay, so that solves the cross-site request forgery problem. This, by the way, is probably the most complicated attack that you'll see and have to try and understand in this course. So if you're not getting it, just think about it a bit more, and of course ask me questions about it. Okay, let's go through sort of the pros and cons of the policy that we've seen, the cookie policy. We'll do it for cookies themselves. Okay, so cookies are very useful, even though there are some attacks and there are some privacy problems with cookies. Cookies in general are a good thing. You want to not type your password in every time you go to a website, right? You want a website to remember that you want the English version instead of the French version. Cross-site requests, even though they sound bad, maybe if you're familiar with cross-site request forgery, they're actually a good thing, right? You want websites to be integrated into each other. You want, if you come to my website, I might embed a YouTube video, right? And so that's fine. You actually don't need cross-site requests to do that. But let's say you watch the YouTube video on my website and you like it, right? You should be able to do that from the website itself. You shouldn't have to click the like button on my video and then YouTube's like, oh, by the way, you have to log in, or we're going to move you over to youtube.com now. Like, it's just like you're watching the video, you like it, you press the like button. It likes it on your account even though you're on my website, right? And the video keeps playing and there's no interruption to anything, right? So that's cross-site requests. So that's what they enable. Okay, so they're a good thing, a net positive for the web. But cookies have problems. So the first thing is if I steal your cookie, it's almost like stealing your password. I can hijack your session. It's not exactly the same because usually some deep administrative things you would have to retype the password in. So if I only am able to steal your session ID, then I won't be able to do some deep settings because it will ask me for the password. And I don't know your password. But and eventually the session ID will time out. And sometimes websites will set it up so that if, like, say I'm in Canada and they know that because of my IP address, and then all of a sudden I'm somewhere else in the world, they might say, you have the right session ID, you didn't ask to be logged out, but just to be cautious, we're going to make you log in again. So sometimes the website just chooses to force you to log in again. So stealing sessions isn't quite as strong as stealing a password, but it's very similar. You can do a lot of damage by stealing sessions. And the difference between stealing them or not is also is a lot of it falls on the website itself, how the website is programmed, which you as a user have no control over, right? So if the website is set up in a very secure kind of way where they're thinking about different attacks and adversaries, then they can really mitigate some of the damage from session hijacking. But there's other websites where as long as you're logged in and have the cookie, you can change any setting you want and they'll never log you out or they'll never require your password. And then the other con of cookies is that you can track users across sites as well. Okay, so that's what I wanted to say today about cookie policies. Next class we'll look at a similar but sort of different set of issues concerning also cross-site kind of requests, but in this case it will be cross-site uses of JavaScript. So the main instance would be you go to Concordia and there's a JavaScript running, but the JavaScript comes from Google. How does the browser figure out different security parameters around that particular thing? Okay, so we'll talk about that next class. So thank you, and I'll see you all next week. Will be the last lecture on security policies, the third. If you recall from last class, we talked about sort of the decisions that were made early in the days of the internet, specifically the what we call the World Wide Web. And so Netscape was one of the earliest browsers, the first kind of mainstream browser. And so a lot of decisions that it made in the mid-90s govern browser policies up to today, although there have been some revisions to these policies. Okay, so last class we talked about the cookie policy that came in 94, and the next year in 95, Netscape also developed a policy for resources, in particular active content like scripting, and how to essentially isolate scripts from each other when you're going to weave together a website that has scripts that are loaded from multiple different sources. Okay, so the name of the policy is called the same origin policy. It arguably isn't the most it's probably not the policy that you would guess if you were looking at it. You probably would guess that maybe it works different than it does. And the reason I say that is because there were a lot of websites that were built that were vulnerable to a particular attack called cross-site scripting. And it seems that the developers did not understand the same origin policy. That's what sort of left it vulnerable. Okay, so just to review again, we have different resources. So we have meta content. So these are the headers. So cookies from last class are in the header. Then we have the actual content of the page. Passive content is basically things that's not code. So it's images, video, audio, the HTML file itself. And then active content is things that actually run. And things that run are a little more dangerous because they can, well, they can do different things. The main thing that we'll concentrate on in this class is if you get JavaScript running, what it can do is it can change the content of the page that you're looking at. So it can overwrite, say, all the images and videos and audio, all the HTML, all that type of stuff on the page itself. What it can't do is it can't really like break out of that web page and do something to your browser or do something to your operating system or do something to your computer. So we're not thinking about like threats like that. Those types of attacks exist, but it's usually because there's some vulnerability in the browser or in the interface between the browser and say a plugin or things like that. So there needs to be an exploit there for that to happen. It's not the case that running JavaScript in a website should ever have any impact on anything other than the website that you're looking at. So once you close that tab or you navigate away from that page, then that JavaScript stops running. And so it should be isolated. We're going to assume that the browser is able to isolate JavaScripts just to the current page that you're looking at. But what browsers might want to do is they might want to limit it even further than that, which is, we'll get into those details. Okay, so the same origin policy, what it says is basically, okay, well, I'll go through the details. So what it does is it sort of governs all the resources on a website. So let's say you go to a website, you download the main HTML file, and then you're supposed to, in order to display the website, you're supposed to load an image from somewhere else and a video from somewhere else, an ad library from somewhere else, maybe some JavaScript from somewhere else. And what we want to know is, are these resources isolated from each other? Okay. Now, if you're thinking of passive content, an image, whether, let's say you download two images, it's not really a meaningful question of like whether they're isolated from each other because they can't look at each other anyways because it's not script, it's not running code. Okay, so the main thing that we're concerned with is isolating active content that is code. So because it's code, it has it can ask the browser, hey, show me the other resource that you loaded, right? And then the browser's gonna, it can at least ask the question because it's active content, it's code, okay? And then what the browser's going to do is it's going to make a decision of like, yeah, I'll show that to you, or no, I won't show that to you. And the other thing scripts can do is they can say, can you rewrite that? So, can you change that resource? So these are the things that are going to be governed by the same origin policy. Now, when you go and visit a website, what the browser does is it writes down every resource, its source, like basically where it came from. So if you download a JPEG, which is an image file, where did it come from? If you downloaded other things, where did it come from? And that's called the origin. Okay, so what the browser will do is it will keep track of the origin. Okay, but how it assigns origins to things is something that we'll get into. It might be a little different than what you expect. Once you've loaded, you don't have to wait until you load them, but as you start loading resources, the browser maintains kind of like a tree structure called a DOM tree. And so everything with one particular, let's say that the website that you're looking at has loaded resources from multiple origins, then the tree is going to have kind of like a branch for each origin. The rule is that, just the capabilities of a script is that it's able to ask the browser to see what's on the DOM tree, and it's able to rewrite things on the DOM tree or add new things to the DOM tree as well. Okay, so that's what the script does. And so what the browser is going to do is it's basically going to say some of the tree you're allowed to touch, but you can't necessarily touch all of the tree. Okay, and so if you get a bad script, because it can rewrite the DOM tree, it can basically rewrite the entire website. So everything, every HTML tag, every image, every aspect of the website could get rewrote by the script, unless if we're trying to isolate the script from being able to rewrite the whole tree. Okay, so getting a bad script on a website that's running it's really bad. It's very damaging to at least the user's experience of what that website is. Okay, so what is an origin? So technically speaking, an origin is a triple. It's the domain that a resource was loaded from. It's the port number that it came over, and it's also the protocol that was used to load it. So the domain is the most important. The other two are maybe secondary. And then there's this override flag as well. We'll talk about that in a second, but forget about it for now. So for example, let's say the domain is test.pulpspy.com. Because it's HTTP, we put that into the protocol as well. And HTTP typically runs over port 80. So you don't normally see that. The browser doesn't show it to you. But if you want to, sometimes you see at the end of a URL, you'll have the domain and then you'll have a colon sign, and then you put in the port number before you start putting in the slashes. So you are able to control ports in URLs themselves. And then this is the override flag that we'll ignore for one slide. Okay, so this is an origin, and a different origin, it would be a difference in any one of these three or technically four elements. So if this switched to HTTPS, it's not the same origin. If it's a different domain or subdomain, it's not going to be the same origin. If it comes over a different port, it's not going to be the same origin. We'll give some examples in a second. Okay, so the same origin just means it's identical. Okay, so the source that you got something from is identical, and the same origin policy is going to say something about things needing to have the same origin. Roughly speaking, it's going to say that if, say, you load JavaScript, it can touch any other resources that was loaded from the same origin. Okay, if it's from a different origin, it's not going to be able to cross over and touch it. One thing you might want to do is you might want to change the origin that you were that your resources are loaded from. Okay, so for example, let's say that you're loading resources from test.pulpspy.com, and you want the origin to appear in the user's browser as just pulpspy.com. Okay, so you can change the origin. The way that you do it is you sort of override the origin that you were assigned. And what you're allowed to do is you're allowed to go up. So if you're a subdomain, you can go up to a domain. If you're a subdomain, you can go up to a subdomain or to a domain. But you can't go all the way up to a top level domain. So you can't say, I want my origin to be olive.com, and I want to be put into I want to have same origin with any resource that was loaded from .com. This is similar to in cookies, where you also can't scope a cookie to a top-level domain like .com. And the reason is it's just too unwieldy because it would match so many different resources. So how you would do it is you would say set document.domain equal to pulpspy.com. This would be allowed if you are pulpspy.com or if you're any subdomain of pulpspy.com. If you tried to do this, say on canada.ca, and you just said, hey, I want my document domain to be pulpspy.com, the browser would not let that get set. Okay, so it would give an error. Now, when you override the domain, then it flips a flag to be true or false. Okay, so what it will look like is when I override it, it's going to be pulsify.com, say it's over HTTP and port 80, and now this override flag is true, whereas before it was false. Okay, so this just indicates that it was true. And so what that means is that resources that were actually from pulsify.com can't interact with resources that were from a different domain, but sort of overrode their domain to match pulsify.com. Okay, so it's kind of a safety feature. Okay, and so you, so you're, if you do this overriding, then you're only the same origins as every other thing that also overrided as well. So if they didn't override, then you're not going to match with them. So let's see some examples. So the first two, we'll compare everything to the top. So is the first two the same origin or not? Okay, so the protocol is the same. They're both HTTPS. The domain is the same. Okay, they're both users.encs.concordia.ca. The path is different. So everything after the slash is different. Okay, so they're not the exact same URL, okay? But remember, in the origin, we just put the domain itself. So the domain is the same, even if the path is different. And so because the protocol is the same, because the domain is the same, we don't say anything about the port. And so the port will be the default port, which is for HTTPS is 443. So in this case, they're going to be the same origin. What about the next one? So the next one is users.encs.concordia.ca. So the domain is the same. However, the protocol changed. So it's no longer HTTPS, it's HTTP. Therefore, they're not going to be the same origin. Okay. This one, HTTPS CISE.concordia.ca, it's a different subdomain. So users.encs.concordia and CISE.concordia.ca. They're different, so the first one will not match the fourth one. And the first one and the last one will also not match, again, because they're different. Now, in this case, it's a parent domain. Okay, so it's encs.concordia.ca. But for same origin policy, what we want is it has to match exactly. So it has to be the exact same subdomain. Okay, so the first one won't match the last one either. So of all the ones on the slide, the only one that matches the first line is the second one. Everything else are different origins from each other. Now, let's say that we do want to match the top one and the fifth one. They're close. They're almost the same. It's just that this one is a super domain of this one. That's where we can use the override feature. So here what I could do is I could set document domain to be, even though it's users.encs, what I could do is I could set the domain to be encs.concordia.ca. Okay, so that's fine. Now, because they're both over HTTPS, because they're both going to encs.concordia.ca, because they're both over port 443, which we'll assume is true even though it's not shown, it looks like they should be the same origin at this point. However, remember the catch that we have that override flag. So they're still not quite the same because the top origin will be HTTPS encs.concordia.ca. Sorry, this is a typo. It should say 443. But here the flag will be set to true because we overrode the domain. Here we did not override the domain, and so the flag will be false. So these documents, they can't talk to each other, or resources across these two origins can't talk to each other. Okay. Now, usually we do this because we want them to talk to each other. That's the whole point of overriding. So there's a simple fix. The fix is that encs.concordia.ca also overrides its domain. Okay, so it also sets document.domain to be encs.concordia.ca. You might think this is pointless because it already had that origin and we're just setting it to be the same origin. Okay, why are we setting it to be the same origin? Well, what it's going to do is it's going to flip this flag. Okay, so the flag is going to go from false to true. Now it's going to match the two, and now your resources can talk to each other. Okay, so there's a lot of grief when you're trying to get resources to talk to each other. And you see a lot of times if you go on, I don't know, Stack Overflow or something, everyone's like, just, the first solution to try is always set document.domain to like the highest level that it can be, which would be concordia.ca. So if you do that on all your websites and you always just set it to concordia.ca, then everything will talk to each other. But there's also the security consequence of nothing's isolated from each other anyways. Okay, so sometimes maybe you don't want resources to be shared, even if they're within the same domain. They're just different subdomains. And so it's a sort of security usability trade-off, usability from the developer's perspective. But anyways, it's very common for websites to just set document.domain to be the highest that it can be, the domain itself. And just run that on every website. Okay, now we're going to go through different ways that you might have, say, JavaScript running on your website, and we'll think about what the origin is. Okay, so I have some JavaScript. I'm at concordia.ca, some website there, and I want it to run. Okay. There's different ways that you can put scripting into a website. Okay, so the first way that you can do it is you can just write it in line. So in the HTML, there's a script tag. So you can open the script tag, and then you can just write your JavaScript, and then you can end your script tag. Okay. So what would the origin? Now this JavaScript is a resource. Okay, so it's considered a resource, so it's going to have its own entry. This code itself will have its own entry in the DOM tree, and we're going to assign it an origin. So what origin would we assign it? So you can think about it, but probably don't have to think too hard, because there's not really two different answers. I mean, we're on concordia.ca. The script is embedded in an HTML file from concordia.ca. It's clearly concordia.ca, so that's fine. So the origin in this case would be, I didn't show the whole origin, but it would be HTTPS would be the protocol, concordia.ca would be the domain, 443. We didn't do any overriding, so that flag could be set to false. Now, another way to load a script is usually inline. We don't like it. The reason we don't do inline scripts is you usually have a bunch of pages that are going to share the same script. Okay, so like say it's like some, I don't know what it does. It does some little thing, but you might have 100 like different pages within your website, and you're running this same script on all of them. Now imagine that you want to change the script. Say some simple change. You just got to change one line of the script, but what you have to do is you have to go and change it on all 100 of those pages. Okay, so it's a lot easier to just host your script somewhere. So for example, let's say it's at concordia.ca/lang.js, and then what you can do is in all your web pages, you can just call that script. Okay, so this is better. Okay, so then what about the origin here? Okay, so concordia.ca is the website that you're on. It's instructing your browser to go to this place and get this JavaScript and load it. Okay, so the origin, in this case, again, there's not really much of a choice, but the origin's either attached to the website that's giving you the instruction to go find this script, or it's attached to the place that you're actually getting the script from, which in this case is concordia.ca. Okay. Now, because they're both concordia.ca, there's not really a question here. In either case, the origin that's going to get assigned is concordia.ca. Okay. But what if it's different? So what if we call a script and it's not hosted at concordia.ca, say it's at github.com. What origin do we assign it here? Okay, so we call this an embedded cross-site script. Okay, Embedded refers to the fact that we're linking to it rather than writing it out in line in the actual HTML of Concordia's page. Cross-site refers to the fact that the script is coming from one place, GitHub, and it's being put into a website that's a different website, which is concordia.ca. Okay, so that's why it's cross-site. And then script refers to the fact that it's about JavaScript. And generally, we don't really think too hard about, like, say if it's an image that gets loaded from another website or things like that. Like, again, we don't need images. We don't really need to think about isolating them because they can't ask to see other things because they're not scripts and they can't run. So it's really, really important, though, to think about what we're going to do with scripting. Okay, so what's the origin going to be in this case? All right, so think about it for a second. Now, there's two answers, I guess. So one is it's coming from GitHub, so the origin is GitHub. The other way of thinking about it is I'm sort of embedding it, right? This word embedding it. I'm embedding it into concordia.ca. So even though it's coming from GitHub, maybe the origin should be considered concordia.ca because it was the origin of the request to get this script. Okay, it's not the origin of the script itself, but it was the origin of the instruction to go in and find this script itself. Okay, so you can see maybe arguments either way. You could imagine that Netscape back in the 90s might decide one way or another. Okay. But the way they decided is actually the one I think that makes the most sense, but it's not the most intuitive. So the origin of this that will get assigned is that of concordia.ca as opposed to github.com. Now let's think through why that is. Maybe that surprises you. If it does, you know why there were cross-site scripting problems for decades, because most people would assume that this isn't the case. Okay, so the mental model for this is what this command does is it says, go over, get this lang.js file. Here's where it is. It's at github.com. But what I want to do is what you're telling the browser to do is just copy and paste the code out of this file and make it just as if I wrote the code myself on my website. So I wrote it in line. I had script, and then I have a copy and paste of the code that's sitting on this file, and then I end it with script. We saw in the first example that when we have inline code, it's given the origin of the page that it's running on. And so what we're saying here is that just because GitHub happens to be hosting this code, it's no different, right? It's just like you copied and pasted that code, and now it's running in the context of concordia.ca. Okay, so when you load cross-site scripts, they're given the same context as the website that is doing the loading of them itself. Okay, now this is important because what that means is that this script from GitHub, it kind of has all the permissions of a script of concordia.ca, which means it can see all the resources that were tagged as origin concordia.ca that are being displayed on this website, and they can overwrite it as well. Okay, so they can change it. So basically they can rewrite the entire page. Okay, so if you get a bad script and you call it and it starts running in the context of your website, it can essentially rewrite it. Now, it's not rewriting it on the server. It's not like your web page is changing it. It's just rewriting it in terms of what the user is seeing in their browser. Okay, so but it's effectively the same thing. I mean, if the user's seeing the wrong website, it doesn't really matter whether it was rewritten browser side or if it was rewritten server side. Other than if it were rewritten server side, it would be more permanent than if it were rewritten browser side. Okay, so so what it can do is it could change the appearance of anything. It can ask to see cookies, although there's some red tape about this itself. And then it can do things like it can log different input fields. So like say there's a username password. If there isn't, it could create it, right? So it could create a field for username password. And then the JavaScript could say, okay, every character by character that's being typed into this password field, I want you to send it. I want you to make a copy of that and send it to a server that the adversary controls. Okay, so getting a bad script running is really bad. Okay, now here's another example. So let's say that we have concordia.ca, okay, and we want to do one of those like Facebook like buttons. We saw them before. We talked about cross-site requests, and so what we want a like button, and if I click the like button, I want it to actually change my Facebook profile, so it needs to somehow be linked to Facebook itself, and maybe there's some information like how many of my friends on Facebook liked this article before, and that's being displayed to the user. Okay, but we also don't want Concordia to know about our friends on Facebook. Okay, so what we want to do is we want to isolate the two. Okay, so the way that we might try and do this, or one way that we could try and do it, is through an iframe. So concordia.ca will load an iframe, and it will say who gets to load that iframe. So it will give control of that iframe to facebook.com. Okay, and then Facebook will send down some HTML, and that HTML basically governs everything that's inside of this iframe. And that HTML can do whatever it wants. It could load more JavaScript, it could load images, load videos, it can do whatever. Okay, say it loads some JavaScript. So the JavaScript is now running inside of the iframe. Okay, so what origin do we assign this JavaScript? And the answer is, this is sort of maybe what we wanted in the previous slide, is that this will give origin facebook.com. Okay, so an iframe is kind of like a mini website. Okay, so the origin inside the iframe can be different. It's assigned basically the origin of whatever is loaded when you load an iframe, whatever domain protocol you're pointing at. That's the origin of the iframe. Okay, so if you want a website where things are isolated from each other, essentially you have to use iframes. Iframes are the tool that you use to isolate resources. So if Facebook is running scripts inside the iframe, it can't like reach out of it and ask about or to see or to change any of the resources that are loaded in Concordia's website, and vice versa. So if Concordia is running scripting outside of the iframe, you can't reach into the iframe. For example, you might say, I want people to like my article, so I'm going to load like a like button from Facebook, and I want to make sure the user clicks on it. So just with JavaScript, what I'll do is I'll sort of reach into the iframe and click the like button. So you can't do that. So the iframe is the barrier that stops those actions from happening. Okay. So Concordia, it can choose to load the iframe, but once it loads the iframe, it gives complete control over everything that's inside the iframe to whoever it loaded, whatever source it's specified for the iframe itself. Okay, so it cedes complete control to facebook.com. Okay, it can get rid of the iframe. It doesn't have to load this iframe. It can change who the iframe points at. Okay, so but once it says, here Facebook, here's a spot on my website, you can do whatever you want in that spot, it has no control anymore over anything that happens within that iframe. Okay, that's solely on Facebook themselves to govern it. Okay, so this is how we isolate resources from each other. Now, sometimes you might want to pass messages or data back and forth. And so there is, with JavaScript, you can do it. But what happens is both ends have to override the fact that it's isolated with a special post message protocol. And so if Concordia overrides it, but Facebook doesn't, it can send the messages, but the browser won't deliver it. And then vice versa, if Facebook allows it, but Concordia doesn't, it can send messages, but the browser won't deliver it. And if they both override it, then through JavaScript, they can pass messages back and forth. Okay, so yeah. Now let's think about cross-site scripting as an attack. Okay, so because this mental model of you know, scripts that get loaded into a website run with the same context of the website itself, that seems like there's some surface area for vulnerability. So attacks are going to be things that exploit it. So there's a couple ways of doing it. Here's some simple ways, and then we'll go to some complicated ways. So a simple way would be if I'm able to somehow change the JavaScript file that's being hosted. So GitHub is a code repository. Maybe I get like the login credentials for a library that's very popular that lots of websites use. If I'm able to change it, then my bad script gets run on every single website that's loading the script from this particular resource. It's given the context concordia.ca. Okay, so hacking a popular JavaScript library, you can do a lot of damage with that. Another thing would be if, let's assume for a second that this script were loaded over HTTP as opposed to HTTPS. Okay, then what the adversary could do is they could, if they were in the middle, they could modify it in the middle. All right. And so you could intercept it, you could change it. And this is why back in when we talked about HTTPS, we stressed the idea that browsers will not allow scripts loaded over HTTP anymore. They will just block that script from loading. And so the reason is it's so dangerous because anyone in the middle, they can modify this script. And once it starts running, then it can modify the complete the user's experience of the complete website. All right, another common kind of cross-site scripting, it doesn't really work that much anymore, but this is how it would work, is let's say you have like a profile on some website and you're allowed to put fields in, like I put my name, I put my, a biography of me, bibliography, sorry, I should say. And then here for my location, instead of saying, say, Montreal, what I do is I put in the command script. And then the tag script, I write some JavaScript, and then I close it. Okay, so I'm embedding an inline script into a text field that I control. Then let's say you come and you visit my website. Then when your browser hits the point where it's supposed to display my location, the idea here is that maybe the browser gets confused. As it's parsing that string, it realizes, oh, there's a command here, an HTML command, and or tag, I should say. But I need to execute that. Like this isn't script to be displayed. This is a tag that I'm supposed to execute. So I'm going to consider that a script, and then I'll run the code that's inside of it. Okay. So then every user that goes to this website to visit my profile website will end up running my JavaScript. What context is this JavaScript running in? It's running in the context of the website itself. So Twitter or x.com, it's running in that context. And then any permissions that you might have that the user, so you come to my profile, you look at my profile, then what I could do is with my JavaScript, because I'm running in the context of Twitter, I could start to maybe make changes to your profile itself or make you tweet things that you didn't want to tweet and things like that. Okay, so we call this, okay, first off, a precondition is that the browser does have to confuse data with code, okay? So this should be data that's just displayed, and even if it was written this way, it should just write out the words, bracket, script, bracket. But we're relying on the browser to not be able to consider this to be text to be displayed, but actually to get confused. We call it persistent cross-site scripting because it's stored on my profile. I'm the one that's storing it. And it doesn't really work that well anymore because we're really, really careful about input fields these days. Okay, so what anyone who builds a website, anytime you take some data from the user and you're going to store it and display it to other users, you're going to probably use libraries and frameworks to do that. You're probably not writing the HTML from scratch yourself. And those frameworks are going to do all sorts of things to make sure that the browser doesn't confuse data with code. And it can do simple things like, for example, it will not allow a triangle bracket. So that it will be like an invalid character. So you can't even or it will look for, a tag like script, and it won't allow that tag and things like that. Okay. So it will do some things to make sure that it's not confused for code, and it will do other things to just make sure that anything that looks like code isn't permitted to be entered in this text field at all. Okay. So anyway, so this problem, they didn't solve the root issue, but they solved it by just doing a lot of sanitization of all input fields that a user may be able to use. Now, I'll tell you one story about this. So in the early days of social media, this attack did work. So there was a website, I might have the details slightly wrong, but I recall it being called MySpace. It was kind of like a social media website, before the kind of modern ones that we have today. And so this attack was possible. And so what someone did is they wrote a script, they put it on their profile, they got some people to visit the profile, it started running the script, and then they were able to use cross-site requests in order to instruct the user who is running the code to basically friend this person's account. So that this person, the hacker, the adversary, became the friend of this person. And also, through cross-site requests, they were also able to make the user that had visited the website change their own bio so that it would also have a copy of the malicious script. Okay? And so basically, imagine 5 people go and visit this one profile, they click on it, then now all of a sudden they have a copy of the bad script. And so everyone that goes and visits one of those 5 people's profile, it recurses. They end up with the bad script as well. And so the bad script just basically ended up it took over the network. So essentially everybody had it within. And there were some problems with performance and things like that in terms of what it did. And if I'm not mistaken, I think the person who did it was caught, and it was one of the early cases of hacking. But I'm a little fuzzy on those details. Okay, let's consider another kind of attack. So let's say that let's just look at this URL. So there's a URL, https google.com/search. There's a query. The search query is script code, close script. Okay. So what happens if you click on this link? What happens if you click on this link is that Google will show you the search results for this search query. It's kind of a weird search query. Maybe there's not going to be a lot of results for it, but it's going to show it to you. Okay. Now that in and of itself isn't dangerous. The URL, the fact that there's JavaScript in a URL, it's not like your browser is going to confuse that with code. It's not going to say, oh, I need to execute this, because it's in a URL itself. It's not even in the content of the website itself. Okay. But what could happen is, let's say the adversary tricks you to click on this link. Maybe they give it to you by email or something like that. And when you click on the link, again, it shows you the search results. Maybe there's no search results. But what Google might do, what they often would do, is they would say, sorry, there's no results for, and then they're going to repeat the query in the website itself. Okay? So they're taking something that was in a URL, and they're sort of copy and pasting it into their website. And they're saying, sorry, there's no results, or there's 10 results, or whatever the number of results are, but it's for this particular search query. Okay? So the thing that was in the URL gets reflected into the website itself, and now it has the potential to be executed. Now that it's sitting on the content of the website, when Alice's browser parses the website and it hits that line, it has the potential for confusing that what should be text, and it might think, oh, that's code. Now I see that there's a script tag. I need to treat that as a script and execute the script itself. All right. So so the search term gets written out into the content of the website itself. We call it reflective cross-site scripting. It works in the sense that the reflection does happen, right? So for example, here I just made something up, and you can see that in the content of the website, it does repeat it. So it does say there's results for this particular script here. Okay. But what happens is that this is coded up in a way that that there's no way my browser is going to confuse this for a script that I'm supposed to execute. Okay. So that's on Google, like for having good security. All right. So, but anyways, in early days, websites like Google were not expecting this. They didn't know that they had to necessarily sanitize these kinds of fields. And so these types of attacks worked for a while. And there was a sort of time period where a lot of people who had social media accounts, they would think that their social media account got hacked because they would go visit it, or one of their friends would be like, why are you posting a bunch of advertisements? And they would go over to the profile, and there was a bunch of ads sitting there. And so they thought, oh, I must have got hacked. Someone hacked, meaning in this context, someone guessed my password or broke into my account. But really what was happening was it was just reflective cross-site scripting combined with cross-site request forgery attacks, where someone was clicking on a link, and then they were being tricked essentially into running some JavaScript, and then that JavaScript was posting things. The JavaScript wasn't able to fetch their actual password itself, so their accounts were still safe. Once they navigated away from the website, there was no control over their accounts after that. All right, now those are sort of two different variants of cross-site scripting, or three if you want to count the just like hack a popular JavaScript library. So there was reflective, there was persistent. When you take a course on network security or web security, it's a web thing, but it usually gets put into a network security course, you're going to see maybe 20 different variants of cross-site scripting. Okay, so there's lots of different ways of executing it. And some of them are really simple. So the ones that we saw are relatively simple. Some of them get really, really complicated. And so my goal here isn't to show you every kind of cross-site scripting attack. You'll see them in other courses. My goal is just to show you why the same origin policy, was confusing and how it led to these particular attacks. And the other thing I want to show you is that the adversary will not, just because something's complicated to do, it doesn't bother the adversary. The adversary will do the most complicated thing possible if it works. If they can make something work, then they're going to do it. So I wanted to show you one other kind of cross-site scripting attack. And the only reason I'm actually showing this to you is because it's kind of on the more complicated end. So I want to give you some of the simple attacks, and then I will also want to give you some of the more complicated ones, just so that you can see that full spectrum, but we won't fill it in with all the attacks that are in between. Okay, so this is what an elaborate cross-site scripting attack would look like. So imagine that you have a web page, and the web page allows you to, again, supply user-supplied inputs. Okay. So for example, here I can type in my email address. This is somewhere I could stick some JavaScript. I could save it. And if I put JavaScript here and browsers confuse that for HTML that they're supposed to parse, then they'll end up running that JavaScript. Okay, so this so far is just persistent cross-site scripting. It's exactly the same. The twist is that some profile things that you set are displayed to other users. You have to display it to another user, otherwise you're just attacking yourself if you're the only person that can see it. And some fields are exactly things that are only shown to you. So when I'm logged in, I can see the email that I registered, but it's not part of my public profile. Okay, so what happened when cross-site scripting became like sort of a predominant way of attacking websites is that they got rid of all the persistent cross-site scripting attacks by really sanitizing all of these input fields. Okay, but some websites got lazy and they said, well, you know what? There's a bunch of fields that are never part of anyone's public profile. Like nobody would ever see that information itself. So we don't have to sanitize those. So we'll leave them till the end. We won't sanitize the stuff that's only displayed to the user themselves. Okay. So there was a lot of administrative panels and back-end types of things that weren't part of a public profile. So it seemed kind of pointless to try and spend a lot of effort sanitizing those inputs. Since it's not like, even if I set it to be some scripting, you're never going to see that script because it's only going to be displayed to me. I could see it, but then I'm attacking myself. Okay, so it's like a self-inflicting cross-site scripting attack. Okay. Now, what adversaries realize is that actually, even if it's a sort of self-inflicting cross-site scripting attack, we can still weaponize it and use it against other users. And we can do it using a combination of cross-site scripting and cross-site request forgery. Okay, so this is the flow of the attack itself. We have a user and she has to get lured to a bad website. So this is evil.com. It's the adversary's website itself. Okay, so this is how it's going to work. And so how that happens, I'm not sure. Maybe a phishing. You click on a bad link, something like that. But this attack would involve you getting lured to a website. Now, normally if you go to a bad website, you know, the web model is set up in such a way that bad things shouldn't really happen to you. You know, it should be safe. Not that you want to maybe test the limits of that, but, you know, in general, like, you know, bad things shouldn't really happen to you just because you went to a bad website itself. Okay. Okay, so this is how the attack would work. So what will happen is the adversary will load an iframe. They'll point it at the social media profile they'll just point it to the social media profile. And what the browser will do is it will go load that social media profile. Because this is Alice's computer, her browser, if Alice is logged into the social media, then her cookie will get sent with this iframe request. And what will get populated in this iframe is her actual profile itself. Okay, or whatever it gets pointed to by the adversary that's loading the iframe. Okay, so the adversary can create an iframe and say, go load this URL. And if it's the URL that corresponds to your public profile, or say your private, like where you would set your profile details, that's the website that would get loaded. Now, because of iframe isolation, this isn't dangerous because, you know, even though the adversary is controlling the outer website, again, they can't reach into the iframe and say, read the contents of your social media or try and change things or try and get JavaScript running in the context of the social media. Okay, so the iframe is isolated from the outer website itself. Okay, but what the adversary can do is, so this is just showing that they can't reach in directly into this iframe. But what they really want to do is they want to be able to do that. They want to, for example, they want to read everything. Say this is your email inbox or something like that. They want a copy of all the emails that are sitting in your inbox. Okay, so what they'll do is they'll load a second iframe. Okay, and what the iframe will do is, assuming that, you know, with RESTful architectures that you're able to say sign a user out just using URL parameters, then what they'll do is they could issue, they could make an iframe like this. Okay, so the source would be twitter.com/profile sign out equals true, and we'll assume that if Alice runs that, again, Alice's cookies go along for the ride, so Twitter knows that it's Alice, and then it will sign Alice out. So she's now logged out. Then what the adversary can do is they can load a third iframe, and these are in order. So you have to load this iframe first, then this second iframe, then this third iframe. You can do that with delays. So you can have JavaScript, you know, wait a few seconds before it loads the next and wait a few seconds before it loads the next. And again, we'll assume that the adversary can use URL parameters to say log themselves in. So they'll pass the username and the password for their own account into the URL. Alice will execute it. You know, people sign, like I sign out of of social media on my computer and then maybe log in with a different account. So Twitter's not like it's strange that someone logged out and now they're logging in with a completely different account. That's normal. It's not an unusual thing to happen. And so what they'll do is they'll log in the third iframe, the profile of the adversary. Okay, so we have 3 iframes. Now, once this first iframe loads, unless if you explicitly refresh it or something like that, the content is just going to sit there. Okay, so Alice's content is still sitting in the first iframe. These iframes just log the adversary out and then log the adversary into the adversary. Sorry, they log Alice out of her account and then they log Alice into Alice's browser into the adversary's account itself. Okay, now you don't necessarily have to do it in 3 different iframes. This is just to make it sort of simpler so that you can see it. Then we're going to assume that the adversary did one of these self-inflicted cross-site scripting attacks where they found some field where they were able to put an input in. They were able to put a script in instead. And when the browser goes and looks at that profile, they execute the script instead of treating it like text. So it's a persistent cross-site scripting. The trick, though, was that it was on something that would only ever be displayed to the adversary themselves. It's not a public profile. It's part of their private profile. But because they logged Alice into their own profile, then they can make Alice look at that profile. Okay, so that's the real trick here, is they're getting Alice's browser to look at a profile that Alice should never see because it doesn't belong to her. It's not her account. It's the adversary's account. Okay, so they're making Alice look at the adversary's account. The adversary's account contains a cross-site scripting attack, persistent, and therefore Alice executes it. Okay, now what happens here? So a JavaScript that's malicious starts running in the third iframe. Okay, the question is, can it reach from the third iframe into the second iframe, or reach from the third iframe into the first iframe? Are these iframes isolated from each other? We said they're isolated from the main website itself, but are they isolated from each other? So to answer this question, we have to answer, well, what's the origin of all of these resources? So the origin of the outer website is evil.com. The origin of the inner iframe is twitter.com. When you load a second iframe, it has origin twitter.com as well, and the third iframe will also have origin twitter.com. The fact that they're in 3 different iframes doesn't matter. The browser just, all it does is it tags resources. So it just says, there's an iframe, it belongs to twitter.com. Oh, there's another iframe, it belongs to twitter.com too. It puts it together as resources that belong to twitter.com that the user is currently seeing on the website. And so the script that's running in the third iframe absolutely can go and it can ask the browser, okay, there's another iframe. It has the same origin as me. So can you tell me everything that's there, right? Tell me all the images and all the text and all the resources that are there. Then it could like package it up and maybe send it off to a server. JavaScript can open an internet connection to anywhere else. And so it could kind of siphon out all of the information from the first iframe and send it off. Okay. Now iframes also, here I showed it as like an actual frame where you can kind of see what's going on inside, but iframes can be 1 pixel by 1 pixel. So the user like has no idea what's happening. They just go to an evil website and there's a 1 pixel by 1 pixel iframe that corresponds to Twitter. So they don't, it's not like they see their Twitter load and then it logs out and then they see someone else's log in. Like they're not seeing anything. There's nothing to see. Okay, it just happens automatically. And here I depict it as they're just loading one sort of screen of Alice's, but in truth they could load multiple screens, right? So they could load a bunch of messages, the inbox and things like that. And then once everything is loaded in the one iframe, then they can play this trick to basically siphon the information out into the third iframe. Okay, so this is an elaborate attack, but at the same time, it sort of shows you the extent that people will go to, adversaries will go to try and attack websites. Okay, so we call this self-inflicted cross-site scripting because you're running a cross-site scripting that only you are supposed to see, but we were able to weaponize it into tricking, like attacking Alice with something, even though that it was stored in our own profile and we were the only ones that were supposed to see it. Okay, here's another kind of attack. So here, let's say that Alice goes to evil.com. So they're on a website. There's an iframe. The iframe is loaded. Inside, there's a like button. And what the adversary really wants is they want to click that like button. Okay? Can they reach in with JavaScript and click that like button? Okay, so we already answered this and we said no, they cannot. Why can't they? Because the frame has a different origin than the outer website itself. So the outer website has origin evil.com. The frame inside has origin facebook.com. And so they're not able to use JavaScript to virtually, reach in. When I say reach in and click it, I don't mean like an action with a mouse or something like that. I just mean, if there's a button, when you click the button, all it does is it sends a message off. So they just have to construct that same message. But they're not going to be able to do it. Okay. So what can they do instead? Is there some way that they can get Alice to click that like button, even though they're not able to do it themselves, given that they control the outer website itself? So the answer is there is at least one way. What they could do is they could take an image, say like claim prize, and they can try and overlay it over top of the Facebook like button. Okay? And the idea here is they're going to try to entice Alice to click on that button, not knowing that there's a Facebook like button underneath. Okay? Now, is a website allowed to do this? Are they allowed to have an iframe and then overlay content on top of an iframe? And the answer is yes. So web standards permit that type of thing. So you can have an iframe. You still control the website. I'm on evil.com's website, so they can do all sorts of graphical things that they're allowed to do. And one thing they can do is they can sort of overlap things on top of each other. Okay. Now the next question is, let's say that Alice actually clicks on this. Is she actually clicking the like button? I mean, the browser is going to be confused because there's sort of a button on top of a button, or maybe this is just an image. But normally if I click an image, like it doesn't do anything, right? And so if I click in this region, the easiest way of thinking about it is, let's say that you put two buttons on top of each other. The user clicks. Which button gets clicked? The top one, the bottom one, both of them, none of them? How do you handle, if you're able to overlay things on top of each other, and when you click, how do you figure out what's actually getting clicked? Okay, and so what the standards allow is they allow the website creator to specify that. So the website creator can choose. Okay, they can't control Facebook. So the like button inside the iframe, they don't have any control over. But this claim prize that they put over top of it, they do control it. It's a resource that belongs to evil.com, not to facebook.com. Okay, and so the other thing I want to emphasize is that, when I drew the iframe and I'm like, you can't reach inside or reach outside, it kind of gave the picture of like the iframe being a border, a graphical border where you can't reach inside or reach outside of like the pixels that are inside of this square. But the iframe is more of a logical border. It just says that all the stuff that's running inside the iframe, you're not allowed to touch. Okay, but it's not a physical border in the sense that you can't, you can't put things over the pixels that you've allocated to this particular iframe itself. Okay. So anyways, back to the clicking. So the user controls this button. Sorry, not the user, the adversary that's creating the website. And so there is an option to make what's called a transparent click. So the click is transparent. What that means is that if the user clicks on it, it just ignores the fact that there's a resource there that's being clicked on, and whatever's underneath will actually get clicked. Okay. So what will happen is, let's say that Alice is logged into Facebook. She clicks on the claim prize. She doesn't know that there's a like button underneath, okay? But her click goes through the image. It clicks the like button. If Alice is logged into Facebook, then her browser is going to make a cross-site request to Facebook. Her cookie is going to go along for the ride. Facebook's going to say, I know who this user is because I know the cookie value. This is Alice. And it already knew who it was when it put this, when it actually populated this, when she first loaded the iframe. But anyways, it's going to say, okay, this is Alice coming back. She just clicked the like button. So I'm actually going to update her profile. And, you know, if it's configured so that every button that she likes, or sorry, every article that she reads online that she likes, you know, it's going to be added to the list of accounts. And then the number of likes for this article, for as far as the adversary is concerned, it will go from 91 to 92, which is good for the adversary as well. Okay, so this is, we call this click jacking. So it's another attack. It's a way to sort of try and get around the cross-site, the same origin policy, but it's sort of a side channel attack because you're using graphical layouts instead of using code. All right, so that was all I wanted to say. So I want to give you some sort of parting lessons from just thinking about the browser policies, both the cookies and the same origin policy. So the first thing is it's sort of hard to get policies right. You've seen that. Also going back to the airport policies as well, airport security, it's easy to have like loopholes in the policies. Once you implement a policy, other people have to follow it. They need to understand what the policy is. So they have to have the right mental model of what that particular policy is. So the same origin policy isn't a bad policy. It's actually it's probably the natural policy. The problem with it wasn't that the policy was wrong. The problem with it was that developers didn't understand the policy. So they thought the policy was different than what it was. They coded websites up in such a way that they were interpreting the policy different, and then that's what caused attacks and problems. Policies in general, you know, there's no great methodology for doing analysis. It's not like code or software where you can, I don't know, do static analysis, or cryptography where you can do mathematical security proofs and things like that. If someone's like, here's the policy, it's really hard to analyze it. The one exception to this I mentioned after the airport talk is you could try to take the policy and turn it into code, into like a series of logical statements. Then you can try and use software to try and go through the policy now that it understands it from a logical perspective, and it can try and find vulnerabilities. So this exercise was done exactly for the same origin policy. So there's a great paper. I should have it in the slides. I don't. I forget. I think it was Adam Barth and Colin Jackson who did a lot of stuff on this. But anyways, they in the paper they use a modeling software. The name of it escapes my mind at the moment as well. But they model the whole cross-site scripting the whole same origin policy as implemented by a major browser. And then they ask the reason, there's like a logical reasoner, and they just say, okay, make sure that it's really impossible, like something that's in an iframe can never reach out of that iframe and interact with the outer website. Or there's a bunch of axioms like that should be true if the policy is true. And what the model found is it found there were all sorts of weird conditions and corner cases and edge cases where there were violations of these axioms. Okay, so there was a weird combination of things that would come together, and then all of a sudden, you know, things weren't isolated that should have been isolated. They found lots and lots of bugs in it. They fixed them all, so it was a good exercise, you know, to do. Another thing is that once you set a policy, sometimes it's hard to change it later. Okay, so now that we have the same origin policy, now that cookies work a certain way, it's hard to, like, you know, you're going to break legacy websites if you change policies. Now, browsers will do this in extreme cases. So cross-site scripting was an extreme case. And so, for example, they made it so that you cannot load scripting over HTTP as opposed to HTTPS. That was a change they made. Yes, it did break websites. There were websites that were loading scripts over HTTP. Now when the user goes to those websites, the scripts don't load, and that's going to break the functionality of the website. And browser said it doesn't matter, like the security is paramount in this case, right? For cookies, for a long time we had third-party cookies. We had cookies that were cross-site cookies as well, and a lot of websites relied on that functionality. And then browsers came along and they said, you know what, we're just turning third-party cookies off completely, and the default setting is going to be that we're not even going to allow cross-site cookies either, unless if a user like explicitly allows it. Okay, and so that's going to break some functionality of websites, and that's too bad, right? We need to improve the security. Then there were, so there's other examples of changes that were made. But in general, you know, when browsers do these changes, they often advertise it years in advance, right? They say, okay, you know, 2027 is the year that we're going to implement this change. You have 2 years to like change your websites, and if you don't, then it's going to break. Another thing is that developers, this is something we saw in usability as well. Users, you know, security is a secondary goal. You want the thing to work right, and then once it's working right, then maybe you think about security after it. And so developers also will do things like set origin to be the most permissive thing possible, set their cookies up to be the most permissive level possible. And, you know, essentially, if you just want to get things to work, you're going to use a lot of like overrides and things like that in order to do it. And speaking of overrides, every time you have like little exceptions, it's like, okay, iframes can't talk to each other if they're from different origins. Oh, but developers want them to, so we're going to add this override. Now you have extra complexity. So now the policy is a lot more complicated because it's no longer that they cannot talk to each other. It's like they can talk to each other in this one circumstance, but generally they can't. And then it becomes even harder to understand what the policy is, and it becomes harder to try and validate it. So complexity is kind of the enemy of security in this case, because it allows for like weird corner cases or edge cases that you might miss. All right, so that's what I wanted to say about policies themselves. And so I'll see you all next week for the next lecture.